Okay. Good morning, everyone. Welcome to the workshop on artificial intelligence applied on offshore renewables or renewables as a general application. So this workshop is organized in the context of the collaboration between COPY and Catapult. We are happy to have here two representatives from Catapult, Ampe Boateng and Edvaldo Mendes. Thank you for coming. And let's start with the opening of this workshop. I would like to invite Edvaldo Mendes from Catapult and Professor Jean-David Capres, who is the academic director of the COPY. Please. Yeah, if you want to have a seat. Yeah, my name is Milad Shadman. I'm a professor in Ocean Engineering Department from COPY. I would like to have a just brief introduction about what we have in terms of the collaboration between Catapult and COPY. Volta para a apresentação, por favor. Vai voltar. Okay. So in 2024, I visited Catapult in Blythe, where they have the offshore house, right? All the big equipments about the offshore wind. So after my visit, we actually organized a meeting, and then we had the first project, the UK-Brazil Floating Wind Research Collaboration. We signed an MOU. I forgot to put the image of the MOU here, but anyway, so it was the first project from November 24 to March 25. Funding by the UK government in the context of Tactical Fund, International Science Partnership. And then we signed an MOU here after that with the presence of the director of COPY. And after the MOU, we proceed with the second project. Yeah, actually, the first project was focused in different aspects of floating offshore wind. Basically, you can see here, concrete platforms for floating offshore wind, AI and digital twin for operation and maintenance, and mooring and power cables. And of course, the last one is the producing hydrogen from offshore wind. So these four aspects that we focus in the first Tactical Fund project. For the second one, it is the ongoing project. We are doing a study supporting the selection of offshore wind zones, offshore wind areas for offshore wind farms session process in Brazil. We are supporting the first round of the actually offshore wind auction in Brazil in terms of the area session. This project is supported financially by DBT Fund, Department for Business and Trade, and started from August 25, and it's our idea is to finish in March and 26, to have a workshop in Brasilia with the Ministry of Mines and Energy and EPE, which is the Brazilian Energy Office. This is an ongoing project. We have, the third one, which is this workshop is inside. It's an activity inside this project. This is the third one. It's AI-driven innovations for enhanced performance and reliability in offshore wind energy systems. So the idea here is to explore the synergies between two institutions in terms of application of artificial intelligence on the offshore wind that cover different areas that Edvaldo will mention after me about these areas that we are focused on. Basically, this was the kind of background of our collaboration. And today, actually, just to conclude, we have this program. We start with Professor Alexandre Evsukov, giving a general overview of the AI application of renewable energy and what we have at COPY. Then we have, it's a 20 minutes of presentation. Then we have 1 hour of presentation from Ampe Boateng from Catapult. It's 1 hour because we had basically, we considered two representatives from Catapult, two speakers, but Ampe can handle both. So we dedicated 60 minutes for his presentation to have enough time to address all the necessary aspects. Okay, so we're going to have an interval and networking after in 20 minutes, and then we have 4 presentations from Ehsan Nikha. He's a postdoc from our group, Gero group. Luis Paulo Assad, Professor Luis Paulo Assad, the presentation. Guy Graça from Matsis. It's a startup that's collaborating with us in different artificial intelligence initiatives, and Gabriel Barros from NACAD. And then we're going to have a wrap-up and the photo and discussion about the future of the collaboration. Okay, thank you so much. I will pass to Edvaldo.
Can you open mine? Just few slides. I translate to Portuguese, but with Ampere here. So again, guys, as previously Milad introduced, we started that collaboration basically almost 2 years ago, and the sign MOU is exactly here, this space, last March last year, and this it started activity collaboration. So as amplified by Milad, so with DBT, Business and Trade Group, we are advancing, almost finalize a project related to slash of areas of construction, supporting the first round of seabed leasing in Brazil, together with Minas Gerais Energy. And this is this one for today that we cover is another fund. So those are funds. Can go to next. It's named Tactical Fund. So this Tactical Fund is second year Tactical Fund. First year we worked together in building a research and innovation roadmap for offshore wind. It's focusing in both countries, so experience from the UK, that's a bit major in developing that farms, and Brazil initiating that. So this was, we mapped it together, and consolidate last year. And this is the second year. So the Tactical Fund approved this project. What is interesting for you to know that Brazil is one of the highest priority countries from the UK perspective, one of the top 3. It's just one detail. This project we submitted last year, among other countries and other projects. And for you to know, this is just the only one that was approved. Means that the importance, the Tactical Fund for the UK government just approved this project. Means that's very, let's say, good, let's say, very attractive of interest of the UK government supporting that. And again, we, in short time, this is just 7 months. Ampere will describe a bit more the advance on that project. But at the end, we are planning to have further. So we want to say, we want to propose further studies, continuing that. This is really important. Think about long term. Let's see, But this is also important for you to know. Share with you these things. How things going? Having support from the UK. Catapult is one of the organizations in the UK that can lead projects worldwide, but also here in Brazil. And that's, as I told you, in AI, for AI, we discussed it in select 6 key areas to advance in that aiming of AI enhancing in reliability and sustainability of offshore wind systems. And the reality of Brazil also is something we are, let's say, addressing. But we have case studies from the data and experience from the UK that we can combine. But applicability of those studies will be can be right applied in Brazil in development cycles. So these 6 items you see, Ampere will go in more details about the advance of that on OEM, for instance, or wake effect. The third one in imports and logistics, digital twinning for offshore substations, and environmental impact analysis also, and the last in concrete substructures, which is also floating. Some of them are connect with the current research from COPI and GERO here. That's why we discuss with Milad having, I'd say, common discussions of some of that. No? You know, this is not only with the UFRJ, also we have another federal university in Brazil that's also partnering UFRN. No? That's why we had a similar workshop in Natal days ago. But it's important. We are, let's say, having with the academy in Brazil a good starting point of collaboration. No? And that's it. The idea is having this chance in this workshop to discuss with you, update with you about that. And Ampere also, we have time to show you our experience and broad view of AI aspects and capabilities of Catapult projects current and previous projects let's say, addressed in this area. You know? So we will combine a bit of general view aspects of AI and the specific of the work package I mentioned, okay? So that's it, basically. That's from my side to save time to Ampere. But maybe now I will hand over to Professor. Okay.
Thank you. Good morning, everyone. Welcome to COPI. I will just present COPI and some of our developments. Oh. Not working? Yes, but it's okay, working, more or less. So really briefly, 5-10 minutes maybe. We are developing solution in partnership with the industry, making innovation in our institute. It's important to speak that we have 13 different graduate programs in COPI, from civil engineering, mechanical engineering, electrical engineering, transportation engineering, chemical engineering, and so on. Okay, you can go ahead. More than 100 labs. We are graduating around 380 MSc per year and about 200 PhD per year. So for South America, we are quite big. We have more than 3,000 students active, 365 professors, more than 500 researchers, and we are publishing about 900 papers, index factor papers per year. Okay, so this is more or less our statistics. Can go ahead. So we are doing both experimental research and also numerical research. And of course, when we can couple both and then create innovation and new products. And okay, go ahead. To enhance and to promote this innovation, we have an innovation entrepreneurship ecosystem. The ecosystem is based on different agencies or let's say groups inside our institution. We have an incubator for startups. I don't know if you will have the occasion to visit that. And also we have an MRAP unit. MRAP is like Fraunhofer in Germany. I know if you are familiar with Fraunhofer, but we try to reach the gap between academy and industry. You can go ahead. We have many partners. Oil and gas, of course, energy, from Brazil, from other countries, China, Europe, France, and so on. Just quickly, some success stories. We have here a small robot that is autonomous, that can travel along pipes. The idea is to be able to make monitoring using AI, onboard platforms or in onshore in complex plants. And that robots receive an award from a national award, really important national award from Oil and Gas Agency. And the robots was able to detect fire, to detect and count how many humans. You have also the possibility to check the position of valves and some manual valves and so on. So AI was used at that time. Okay, next. Another project using AI. This is a project where we have a autonomous surface vessel coupled with a drone, let's say, and both of the systems are using AI. We developed the upper part, the drone and algorithm to land and also to recognize oil spills. Okay. Another project that is additive manufacturing, and the idea is to be able to using AI to predict the distortions that you have using additive manufacturing with metals. And the main idea of that project was to be able to produce complex parts on board platforms to replace the parts without to wait eventually weeks or months a part to arrive. Okay. And maybe finally, or almost the last one here, it is another project. This is a pig to make low-cost detection of illegal tapping and corrosion inside the pipes, okay, pipelines, rigid pipelines. And AI has been used to detect the patterns of that corrosion and eventual patting inside the data collection system. Can go ahead. And I guess that is the last one. This one is our ocean lab. This is of course a real one. So we can, at the upper right corner, you can see the video of FPSO. But we have also a digital twin linked to that to reproduce the data that has been generated during the real experiments. And then of course we can couple AI algorithm to that data. We have projects trying to predict the, let's say, the failure of anchoring lines, for instance. Another couple of projects on detecting, but it's not linked to that data, but corrosion using drones, so monitoring of complex offshore systems. Using visual computing, we also have projects on detecting anomalies on underwater complex structures or pipelines. Okay. So that was my short presentation of the institution.
Thank you, Professor Jean David, for covering all the AI initiatives that we have at COPY. Thank you, Edvaldo. Let's move to the next block, which is starting with two main presentations from Professor Alexandre and Ampé. So first, I would like to invite Professor Alexandre for his presentation, Application of AI in Renewables.
Thank you. Thank you, Milad. Thank you for invitation. So, well, my name is Alexandre Sukov. I'm a professor here at Civil Engineering Department. And I will present some of the projects we have been conducting here at COPY, partnership of our colleagues in the lab, about the application of artificial intelligence in renewable. So, yes, just to make a bit of context, artificial intelligence is a big name, renewables also a big field. So we are now just focusing in forecasting models for wind and ocean and so on. So it's more or less what I will present here. Just some institutional. Qual é aqui o Milad? Esse?
É, isso aí mesmo.
Para onde eu tenho que apontar? Okay, so Genevieve has presented our institution. We have 13 departments, 13 graduate programs in engineering, but we have also some transversal areas, several transversal areas, and I particularly attached to the computational science and engineering transversal area, that we bring together a lot of researchers working in numerical methods, artificial intelligence, digital technologies, and so on. So it's a very intense group that we have very close partnership in several initiatives. And well, here is our lab. We are in this beautiful building in the technological park. We are divided in 8 research groups: computational mechanics, geophysics, environment modeling. My colleague Luis Paulo will present after. Artificial intelligence, scientific visualization, digital rock, remote sensing, and Earth observation. We have also several facilities. The UFRJ supercomputer is installed in our building, Lobo Carneiro. We have some facilities of Earth observation and remote sensing, also visualization facilities. And yes, we have a visualization center. Yes, that is in our building. Then 9 in 10 visitors go there to see this standard program. Go to the visualization center and ocean lab that is in front of. Yeah, so you are welcome if you want to go there. So yes, okay. We have also this human research program founded by ANP, the Brazilian National Agency for Oil and Gas. This is a multidisciplinary program. This is a program, ANP program, that provides scholarship for the students to work specifically in themes related to oil and gas industry. Our program is related to digital technology, so it's very, very large. So I apologize, this slide is a little bit old, because now we have, in the first version, we have 7 engineering programs, 4 engineering programs, and then we updated to 7 graduate engineering programs, and also 7 undergrad courses. So we have a very broad, different courses and different kind of formations in our program, and we get students from different areas, and it's very nice because some projects different students in different areas can work together in very complex programs, right? Also, we have finishing. Maybe first class will be offered this year. It's an online course of artificial intelligence. It's a graduate. We call here in Brazil lato sensu. It's like an MBA style. It's a specialization on artificial intelligence, online, full online, and it covers data acquisition and cleaning, machine learning, deep learning, computer vision, natural language process, several applications in business. We can, well, adapt those applications according to different interests of different partners. And we hope that we will offer this course this year, first class this year in Brazil, as an open online course. And this course has some particularities, that as we are an engineering school, right? So we focus artificial intelligence from the engineering point of view. Because now we have artificial intelligence, this hype of artificial intelligence. Everybody uses ChatGPT, and everything is large language models. But we see that many other applications of artificial intelligence for engineering, and then this course is more or less focused on those kind of applications, right? We have also here a Center for Artificial Intelligence in Renewables that was approved by FAPESP. FAPESP is the research agency for São Paulo State, but they have a lot of money. And they are also manage the funds of the Brazilian Internet Committee. So they open some editals, some call of offers for different centers in Brazil. So we get this one in Rio, there is another one in Ceará, one in Minas, I think. And it's also an interdisciplinary center. We are organizing it in 5 work groups for different applications: wind, solar, biomass, and hydrogen, and one like transversal work group for digital technologies like machine learning, high performance computing. There are several Brazilian and foreign institutes participating, also some companies that are in partner in this project. So for the projects we are going on in the lab, we have here this one project that intends to make like a digital twin of the South Atlantic. My colleague Luis Paulo will talk a lot of that. The idea is that we have some global models, but for operation and wind turbines and also other oil and gas operation, we need more regional models, right? Small scale grid models in order to be able to make those operationals. So we are trying to make several regional grids. We have been working a lot in this Southeast Brazil. I'll show you some results, but we also working on other grids in South Atlantics. And it's very time-consuming, expensive, computational expensive to produce those regional grids because, you know, numerical models, and you run to a lot of models. So we are attempting to make some other low-cost computational, low-cost models using artificial intelligence. So this is one of the most, what are mostly interested by now. So as I said, in the lab, we have a lot of work in remote sensing also. And then people from remote sensing are able to, based on images of remote sensing, particularly radar images, they are able to estimate wind. So also there is some working projects on this area. So here you see the comparison of the speed estimation by the remote sensing images and the speed observed by the buoy in the field, right? So you see a very nice connection between them. So you see that we can have a very good estimation of wind from remote sensing. So right, this is one of the results that we were working. And for the forecasting, well, forecasting there is a lot of methods for forecasting. When you have one-dimensional or short-term forecasting, there is a linear models that can work very well. So here we have wind forecasting, 1D wind forecasting. For instance, if I want to forecast the buoy measurements, and what we can do, if you want to make a 24 hours forecast, we can do 24 models, right? Each model forecasting one day ahead for 1 hour. For instance, you have 10 a.m., then you forecast 10 a.m. for tomorrow, 11 a.m., 11 a.m. for tomorrow. So you have 24 time series, and each model will forecast the 1 day ahead for the next step. And this works pretty well. Here is the comparison RMS and R2 of the models. This is for 2 velocity components, U and V. It's very usual in this. And you use this very well-known autoregressive structure for linear models, and it works very well. Here you see the predicted and observed velocities and correlations. So it works very well. One-day forecast, it's no problem. But when you need larger horizons, right, in 2 days, 3 days, 4 days, so for wind, it's a very different problem, much more complex. So we need more powerful models. So our first attempt to do that was in 2020. We made a model for nowcasting, still short-term forecasting, but not for wind, but for rain. But the good thing in artificial intelligence is that the same model you can use for several applications. So the same model that predicts rain, you can adjust it to predict wind or whatsoever. So this one is to predict rain based on a radar image. As you know, Rio de Janeiro suffers a lot with hard rain, so it's a very big problem for us. So we need a good nowcasting. And sometimes there is a very particular event that there is a very large tempest that coming, and then the mayor suspend activities in Rio de Janeiro, and then the rain goes to the ocean. There is no rain, and everybody was happy. That was a holiday. And so that's why nowcast, and the better you can forecast rain is very important here for us. So, but as you see, same things happens. 30 minutes forecast, very good result, but when you horizon going larger for 1 hour forecast, not so good. So the challenge here is to get good forecasts for long horizons, right? And well, so as I said, we have been working a lot on those grids in southeastern Brazil, and one of them, this multi-resolution southeastern South Atlantic data set, that we have 3 grids here centered on near from Santa Catarina state. Have a very high resolution grid, then a medium resolution grid, and then a low resolution grid here that covers all this area. And then we have also 2 layers of SAR images in the same regions, so that you can make several works for this. This is a data set that is available, publicly available. So we, in our group, we are very concerned to make data set available for research. So this is data set available in Harvard Dataverse that will also a paper that is going to appear in Scientific Data Journal. And then we make several comparisons. We have that information for the Buyot. We have the comparison of the wind prediction and the SAR predictions here, right? The wind speed. And then here is some snapshots of the results of the models. So there are lots of work that we can do. We can try to do super resolution. For instance, you have a large data set and a large grid and make a regional grid, right? By artificial intelligence, you can make forecasts. There is a lot of work that we can do with this kind of data set. I will show you some examples of what we have been done, right? So what the work that we made from the same data set that I showed you before is the downscaling, right? Downscaling has a lot of names. People from meteosonography call it downscales. We call it super resolution. So it means that you have a grid, low resolution grid, then you have to compute a high resolution grid, right? So it's very difficult from numerical problems that consumes a lot of computer power. So we try to do it more faster with artificial intelligence, but, well, how is it? But ocean is not very predictable, right? Ocean is very hard time to make super resolution in the ocean. So in this work here, we show that we have a better solution inside land than inside ocean, right? So as inside the land you have the relief, the mountains, and also it creates a pattern for the model to recognize. So it's easier for the model to make downscales under the land than in the sea. The sea is very chaotic. You can have any kind of movements in the sea, so it's very hard to make downscale above the ocean, right? So this is also a paper that, well, it's in preprint, but it is under review for a journal, right? Then we have some results for forecasting. We have forecasting for wind and forecast from the ocean. First one is for wind. We use results from the WRF model. WRF is very well-known model for weather model. So we use 3 types of model. We use some standard fully convolutional model, some more complex recurrent dynamic model, and also a more complex transformer model. So each model has one characteristics. This one is like autoregressive, but with convolutions. This one makes some dynamical computation. It's a recurrent model, right? It's based on LSTM. And this one is a transformer, and it's very well known transformer, that large language model, but it's also used for computer vision also. And the idea here is that the transformer, differently from the convolution, because convolution has a filter that goes in the image like that, and the transformer is quite different. The transformers see all the image is in one time, right? So it takes the image, it split the image in several parts, and then it processes each one of the parts, and then bring everything together. So we have some results, and well, results, it's for each one of the models. We see that we can, well, predict somewhat, but the same thing happens as the horizon grows, the errors also grow. So it's a problem that we are working on. But you know, for short-term nowcasting, it works very well, but for other horizons, not so well. And the good thing is that same models, we can work in different applications. Here is Ocean Brom's model forecasting. So this is the arrow. Good thing here is that the arrow kind of stabilize after some steps. And here is the best error. We found the most errors near to the shore, and low errors away from the shore, so it could be nice for offshore operation, right? So this is also work that is, well, this is a thing that is good for artificial intelligence, and then you have one model, then you can use it in different applications. So it's the same model you have used for wind. So this idea of forecasting, weather forecasting, is a very active topic in artificial intelligence research right now. We have several different models that you can have in the internet: forecast, GenCast, Mesh GraphNet, GraphCast. Well, you name, there is a lot of names that are going on, but mostly they work in global weather, right? Global weather with large grid. There are some attempts now that makes a smaller grid, but for regional models, you need smaller grid. So our research focus here is smaller grid, regional models, right? Long horizons, and mostly for South Atlantic, because most of the application that you see a lot of application in China, US, Europe, but not so many in South Atlantic. So we are focusing in our here, South Atlantic. So that's it. Thank you very much. And if you have some questions.
Thank you. Maybe we have like 2 or 3 minutes for 1 or 2 questions, if there is any. Yeah.
Hello. Asking in English, else?
Portuguese or English? Introduce yourself.
Okay. I'm Lucas. I'm a master student here in PESC, I'd like to know if you have worked or have you seen some works on upsample of time, not spatial, like the downscale application you've presented, but have you seen works on upsample of wind data in time, like taking a wind speed telemetry with a low sample frequency and then upsample?
Upsample generally is easier than downsample, right? So upsample just sum everything. If we make linear interpolation, it works not so bad. But because when you make downsamples, right? Make downsample, you have to infer high frequency.
Yeah, downsample. Yeah.
You make downsample. You have a larger sampling rate, then you need a smaller sampling rate. So this is this is a problem, right? Because you have like to infer things that you are not looking for.
Yeah.
So that's why the problem in the wind over the sea is because the sea is very chaotic. It can change a lot. Then you do not have patterns for the model to understand.
Yes.
But there are a lot of tools right now that is devoted to make this kind of problem and more general problem that we call inverse imaging, right? That is inverse problems in imaging, which super resolution is one of them. And they are using a lot these diffusion models. So if you want something to study in this subject, I think that diffusion model is a good start point. There is a lot of models that have using diffusion models for different problems in imaging. Super resolution, one of them, but masking, the blurring, the noising, and other kind of models. Also there is just one that appears last year that makes a weather forecast based on diffusion model.
Okay,
Diffusion model now in artificial intelligence is one of the hottest topics in the artificial intelligence.
Thank you so much, Professor Alexandre, for your presentation.
Okay.
Let's move to the next presentation. I would like to invite Ampe Boateng from Catapult to do the presentation. Thank you.
Good morning, everyone. Well, thank you very much for coming here, and thank you very much for hosting us here as well. So my name is Ampere, so I'm from the Offshore Renewable Energy Catapult. So I'm going to give a bit of a long presentation, but I'm sure I'm going to try to go fast, but if I go too fast or if you've got any pressing questions, feel free to mention that. So I'm going to first introduce, maybe I'll just use the buttons, yeah. So I'm going to introduce ORE Catapult at first, but once again, I'm going to go through it very quickly. So ORE Catapult, we are a research and technology organization in the UK. So I think there was made mention of Fraunhofer centers. Basically, we are just like Fraunhofer for the UK. We aim to bridge the gap in between academia and industry. And we work quite a lot at some of our missions are highlighted here around de-risking new technologies. So we've got things like testing assets, which help in de-risking those. I will show a little bit of an image of some of the testing assets, but as you can see, we are based all over the UK. My office, mine and Edvaldo's office, is in the National Renewable Energy Centre, pointed there, but we do a lot of work all across the UK. So we've got testing assets. This is our 7 megawatt offshore wind turbine. So that is a mainly research asset. So it's a 7 megawatt turbine, which we use for a lot of test research activities. We've also got loads of other facilities. So this is our blade test facility. So we can test up to like some of the biggest blades in the world have been tested here, over 100 meters long. This is the GE's 15 megawatt nacelle, which was also tested in our facility. So today I'm going to be talking about AI, but that is not all that ORE Catapult does. We cover a lot of different areas, so I've highlighted a lot of some of that here. A lot of the work I'm going to be talking about falls under smart O&M, but that is not the only bit of work we do. So if you've got any thoughts, any ways of collaborating around all these different areas, we are more than happy to engage and collaborate. So my presentation today is mainly going to be focused on AI and AI applications in offshore renewables. And basically, AI digitization as a whole has a big role to play in offshore renewables. So it could play a great role in every stage of offshore renewable deployment, from site selection all the way to decommissioning. However, a lot of the activities that have been already used and successful in the offshore renewables industry is in the area of O&M, operations and maintenance. So a lot of the presentation, a lot of the slides I'm going to present will fall under that. So as was mentioned earlier, AI is a very broad topic and it covers a lot of different areas. There is the large language models, which people talk about, very much talked about by everyone. That is one type of AI model, but AI can be applied in so many different areas, as I've mentioned already, around environmental monitoring. So this is sort of like some image showing where we can use that. We can use AI for design optimization and so many other areas. Because of the lack of time, I'm going to move on and talk about some of the different branches. So AI basically has many, many branches. A lot of the work that has been done in offshore renewables has focused on machine learning, but all the different areas have also been covered. A lot of the work that I will talk about, once again, will fall under machine learning because that's the very common AI approach which is used. So I included this slide just to explain a little bit. So as I said, AI covers a broad area, and there's a lot of research papers, reviews, which look at AI application in offshore wind, for example. So this covers all the different, some of their papers, which cover some of the different applications. But in this particular presentation, I want to more or less share our experience at ORE Catapult. I think if you're looking for broader experience in the offshore renewables, there are loads of review papers which go through the different reasons, different applications of AI. So I've shown some of them here, including things like fault detection or prognosis, diagnosis. And once again, also want to show how the AI, the number of papers written in AI has been, for offshore renewables, has been increasing over the years and will definitely show loads of strong progress in the future as well. So once again, in the next slide, I'm going to be focusing a lot more on some of our experience with AI in offshore renewables. So, as I mentioned earlier, machine learning is one of the biggest approach used in offshore renewables. And this slide shows a little bit of an example of how we've applied machine learning for generator condition monitoring. So in this example, I just want to show our typical workflow that we use, including getting the data, cleaning the data, preparing it, training the model, testing the data, and number 5, which is improve. That is one of the critical steps, because typically you make a model and you get more data coming in, and it's very important to retrain the model over and over as more data comes in from the existing wind turbines. So the example I've included here of how we've used machine learning in offshore renewables, this is neural network models that we generated for predicting converter health. So the way that we use a lot of machine learning algorithms is we aim to use that to generate different levels of alarm. So for example, we need to make sure that a component, for example, is operating under normal operation, or in faulty condition, or in a condition which needs a bit of looking at. So for this example here, we created using a neural network model, and we monitored the residual, so the difference between the actual measurement and the model's prediction, and that is able to give us an indication of the component's health. And we apply these categories as shown here. So for example, if you've got different thresholds, if you've got a high residual threshold, then basically you raise an alarm. And if you've got a low residual threshold, then you don't raise an alarm. One of the critical inputs that go into making such decisions is having very good and clear understanding of the engineering behind all that work. Because if you don't understand the engineering of how the converter works, relying on pure data science is not necessarily going to let you understand if a threshold value is reasonable or not. So our focus mainly is on combining a lot of the data science approaches to machine learning, but we also have teams dedicated to engineering and engineering design who are able to contribute a lot of input into understanding how the components themselves work. Okay. So this slide also I included this slide to show some of the different ways that we use machine learning as well. So these are the classical categories of machine learning algorithms, so clustering, regression, and classification. And we use all these different techniques. Sometimes we can use all these different techniques in different ways in the same project to solve problems. So this is an example of how we've used clustering to identify different operating conditions. In this case, we use that as part of our data cleaning process so that we are able to identify different operating conditions for this, which is a model we created for wind turbine pitch system. So that allowed us to improve the model performance and also get better prediction output. So we then moved on to use the same kind of residual type approach in terms of making predictions. So that approach used an actual regression model. But as I mentioned, we used like the combination of both in making that. So just want to point out that we don't have to use one particular algorithm. We don't have to use one particular technique, but we can use combinations of them in doing different sections of our modeling. This slide also covers different projects that we did looking at pitch bearing remaining useful life. So understanding the remaining useful life of components of a wind turbine is very important. It's very important because you need to make decisions on how you maintain them, and also you need to, especially at the end of life, you may decide whether you want to repower or whether you want to do a life extension, and it's very critical to understand how much life is remaining in the component, so you decide whether you're going to maintain it or you're going to replace it. For this particular project, I included here just to show a little bit of the process of how we develop some of these AI-based algorithms. So for the pitch system, apologies, I hope you can hear me all the time. I know the mic keeps going in and out. Okay. So the pitch system is part of the wind turbine which controls the blade's motion, and the pitch bearing basically allows the blades to rotate. The loading condition for the pitch bearing is very complex, like shown here. So they are radial axial moment loads, and it's important to understand the loading condition in order for you to understand how the pitch bearing is being loaded and how it's degrading. Putting sensors all around the bearing will be very challenging, and in a lot of cases, we did this project for an actual offshore wind turbine. It's very impractical to put sensors all around. It's very difficult to also necessarily measure some of these quantities. So in this particular case, what we did was we had to combine two different approaches. So we combine simulations, which allow us to understand what is happening at the local level, and then we use machine learning to kind of extrapolate that on a bigger scale. So this gives a bit of an example of some of the simulation models, and from the simulation model perspective, you're able to apply engineering, typical engineering approach of understanding how the pitch bearing moves and how much damage is occurring. So we categorize that based on different cycles, matched with all the different loading conditions. So this is one of the moments, the edgewise moment from simulation, and we're able to use a machine learning model to learn the pattern that is being generated from the simulation, and then extrapolate that onto the normal wind farm. So as you can see, this simulation is being done on a much higher resolution, but the inference from the actual wind turbine is done based on scatter data at 10-minute intervals. So that gap in between, that 10 minutes, we basically fill that from the machine learning algorithm which is trained on that. So that has successfully been used or been used to demonstrate some of the outputs, where we're able to demonstrate the damage that is happening over time in our pitch system. So you can have it along the time this way. This helps you improve your operation, because if there are particular times where the pitch system is incurring a lot of damage, you're able to adjust your operation to limit how much damage you're basically incurring over that time. But you can also accumulate all that damage in a trend like this so that you know your remaining useful life. So that is some of the experience I wanted to share, because we're not necessarily we're not necessarily following purely extracting data from wind farms. Sometimes we need to use simulations to bridge a gap in between the data that we have and the data that or the output that we need. So this is another example of an algorithm. So the other one was for the pitch bearing, and this one algorithm we made for the pitch system as a whole. So for the pitch system as a whole, it's got so many different components. It's got pitch inverters, it's got pitch motors, and the owner of the wind farm doesn't necessarily want to install sensors everywhere, but wants to get a very good idea of the overall behavior, the overall health condition of the pitch system. And so what we did was we took some SCADA data of the blade motion, some of the pitch inverter current, some of the pitch motor temperature, things like that, combination of them, and created models which were able to make very good predictions of the pitch system health. One of the things I want to highlight here is what I mentioned earlier about the use of clustering. So one of the things that we came across when we were basically developing this was we found out that the turbine is operating in different operational modes, and that was having a very big impact on the turbine output and on the model output. And so we were able to use some of these clustering approaches to basically create additional features that go into the model. And once we were able to create that based on the grouping here, we were able to have additional features which improved the performance of the model significantly. And as I have here, this is one of our most successful tools that we've developed. So it's been used on actual wind turbines, and it continues to be used and detects faults. So I think that pretty much covers a lot of the, So that covers a lot of the application of machine learning. That focus is mainly on fault detection, component health analyses, remaining useful life. So we do a lot of work in that area. I've only shown just a few components, but there's a slide down which will show all the different components where we've used similar approaches to basically monitor the health of the different wind turbine components. But I want to shift to a slightly different application, and this is where we use different forms of AI, especially image-based AI, to help in the solving problems in the offshore renewables. So one of the problems that we've used image-based AI to help us is for the detection of these things called water trees. So what you have is wind turbines need cables which transport the electricity from offshore to onshore. And one of the problems they often have is they get damage in their insulation. These are called water trees. These are very small microscopic damage that occurs in the cable. And some of the work that we've done in the past is we do a lot of testing of these cables to find out their resistance to water trees. But what you need to do is you need to take those samples, and you'd have a person, a human being, under a microscope, investigating and finding all the different water trees. So that process is very long, it's very tedious. So what we've done is we've basically developed AI models to help us to detect the water trees. And basically we had a human expert who is able to verify and allow us to check the performance of the AI model, and it's quite a successful tool. So another area, the image doesn't quite show it so clearly, but another area where we've used AI from an imaging perspective is to help detect leaks. So in one of our testing facility, we are testing seals for bearings. So the seals are supposed to keep the lubricant in the bearing inside so that it's able to lubricate the bearing. But you do get a bit of leakage from the seal. So while we're carrying out testing, we need to monitor the leakage of these seals. But we're not able to do that. You can't do that with a human being watching a video 24 hours. So we're doing the testing 24 hours continuously. So we had to develop a tool, basically, which continuously technically watches what the live feed and basically detects where there is any leakage, records when the leakage starts, and basically helps us with understanding what's happening during the testing period. So even if the leakage starts at night, you're able to detect that and make the necessary recordings. And I think my other slide here is on how we've used image-based AI for casualty detection. So for offshore wind farms, you have O&M operators or O&M technicians who go into all these offshore wind farms and they carry out all the O&M activities. What sometimes happens is a person may fall into the water, and it's very critical that if someone falls into the water, they are found very quickly and rescued. Even though people go into the water with survival suits, surviving in, for example, the North Sea in very cold waters for a long time is very difficult. So it's very important that if someone falls into the water, you can find them quickly. So we worked with a company who are developing a robot, essentially, an autonomous vessel. So this autonomous vessel will find people in water and then rescue them. And as part of this, the focus that we were looking at is how can we improve the detection of the casualty in the water. And the approach that we used was we had to combine RGB, which is normal camera footage, with thermal image footage into like a fused image, and that basically improved the performance. So I've got a video which just shows some of the detection that we had. So this is not an actual person. This is a bit of a trial we did. We put like a jacket on a dummy and pushed it into the water, and then had a drone would basically circle and to detect. So one thing that we found is that during the day, if it's nice and bright, basically you get very good detection with just the RGB. During the nighttime, when it's completely dark, maybe you get better detection with the thermal. But there are those transitional periods at dusk or dawn when there's not enough light, but it's not completely dark. And so that's where the fused image basically performs the best. Yeah, so basically this is a kind of retrained YOLO model. So we just retrain the top layers with our own footage from the Fuse model, and we're able to get some very good outputs from there. So another area, so we've talked about large language models. So another area where we've done some work on is how can we use large language models. I will talk later on about some of the work that we are currently ongoing around environmental impact assessment and the use of LLMs there. But some of the work we've done in the past is how can we use these LLMs to basically go through our maintenance records, maintenance reports, so that we're able to understand what's happened. And the key reason why we developed this LLM is we found that we've got loads of data, scatter data, but there is no context to the scatter data. So maybe someone has gone and carried out some O&M activity, but it's not shown in the scatter data. So what we did here was we used the LLM and ingested a lot of the O&M data, and then we're able to query those LLMs and then get it to give us additional context so that we can create different features that we add to the scatter data, and that allows you to identify areas or time where there's been O&M activity taking place. So if the scatter data is a bit abnormal and you're carrying out an anomaly detection exercise, you will probably pick that up, but you can understand that is through O&M activity rather than the turbine itself. I will skip over these because, but we've also done some work in the past. So this is more or less around modeling of floating offshore wind turbines. So, but we use typical machine learning approach. So here we use a bit of LSTM and in some cases XGBoost as well. Some of the challenges that we had there was to do with how do we select the training windows, particularly the outputs that the inputs that we used here are inputs from OpenFast. So this is simulation, and so you have chunks of simulation. So how do you make sure that you put it together so that you are still able to make better predictions? So I think I will skip over that and get to this. So, as I mentioned earlier, we've used a lot of machine learning to develop different models for monitoring components of wind turbines. So I've talked a little bit about some of the pitch bearing but we've in converter health, but we've got so many different models we've developed mainly to monitor components, and most of these basically use machine learning approaches, but also we add the additional information in terms of you have to have good engineering understanding so that if you do anomaly detection, if you detect an anomaly, you understand that it's an actual fault, not like I said, O&M activity or something which is not a problem. Yeah, so another part that I wanted to share is, as I mentioned, for us at ORE Catapult, we sit between sort of academia and industry, and a lot of the challenges we face are linked to practicality and some of the industry demands. So one of the key things here is that in industry, what we find is typically most wind farm operators or owners want to use 10-minute SCADA data. They don't want to add more sensors. They want to use the sensors that they have available, and they want you to make it work. So often you will have to either use virtual sensing or some other technique to help. So our focus is to make sure we are relying on the data that's available, not needing any data. Another thing that a lot of operators want is they also want you to focus on alerts or warnings. So it's not necessarily that the key output they want is to understand if something is wrong, not necessarily to generate a graph which explains. So typically you would have to, we would put things in the context of alarms, and also generate like reports, which an operator may choose to read or not, but you can put the technical information into the report. And there's a lot of work on how to make things flexible. So a lot of these algorithms we've developed, we've basically implemented them in the cloud so that it's accessible, and you can also have like edge solutions for that as well. So I think this broadly covers some of the experience that we've had in terms of using AI in offshore renewables. My next slides are going to be focused a bit more on the collaboration that we have under the UK Brazil Tactical Fund. So I'm going to move on to that next. So before we move on, I want to just give a bit of a broad context to this tactical fund. And I want to show that with basically what the vision and what the vision for our team at Already Catapult. So we've got a digital and robotics team, and our vision is to basically help create efficient O&M activities. So we want to focus on using digital twins of components, just like I mentioned, to help with O&M activities. We also want to help with O&M activities in terms of weather impact analysis, vessel tracking, and also the use of robotics. So that is the general vision, but the avenue or the mechanism that we want to deliver this is through the use of digital twins. So there's a lot of talk about digital twins. What are digital twins? Or so many different descriptions of what digital twins are. In our opinion, digital twin, the critical aspects for a digital twin is that you have to have a physical asset feeding information into a virtual asset, and that also feeds information back into the operation of the physical asset. So you have to have a complete loop of information flowing through from the physical to the digital. In order to achieve this, you need a lot of infrastructure, you need a lot of capabilities. And I think these are some of the ones I've highlighted here around the things that you need in order to have a fully developed digital twin. So you need data service, you need some kind of user experience, you need integration, management, intelligence, and so. So this slide is basically showing exactly what I've been talking about with the requirements to get a developed digital twin. This basically is called the periodic table for digital twin. It was developed by the Digital Twin Consortium, and it basically highlights all the different capabilities you need to develop in order to have a digital twin. So for our vision is we want to have a digital twin. But as you can see, there are so many of these different tiles, different capabilities that we need to have. We understand that we cannot achieve all these different capabilities. So we need to work with other people, find partners, so that we're able to develop different parts of this, collaborate together, and we can bring it together in making a full digital twin. And that brings us to our current project. So the current project is a very short project. So we basically scoped it out to start in September, finish in March, and it covers 6 different topics, which I will talk about in details. But the whole point here is that we want to show different proof of concepts within this short space of time of how we can generate examples of those different types of tiles which fit into the digital twin, which enables us to carry out a lot of activities. So, as I mentioned, as been mentioned before, we already have an MOU signed with UFRJ. So it will be fantastic if there are different areas that we can collaborate on and kind of work together and develop more of those capabilities for building those tiles. So I'll move on quickly to talk about the first topic, which is on AI for operations and maintenance. So, as I mentioned, we've developed a lot of tools like this for monitoring different components of the wind turbine. These work very well by themselves. However, typically, what the operators want is they want more information in order for them to actually take actions. So if you say that a component is faulty, they want to know, can I repair it? And that is where the first of the sub-projects aim to help. So we aim to help with that by developing a simple model, just as a proof of concept, which helps you detect or determine weather windows, whether you're able to carry out O&M activities or not, when you have an algorithm operating in conjunction with the component fault detection. So basically what we propose is we want to identify this kind of weather window where you can carry out O&M activity. But there can be different O&M activities that you carry out. Some of them will be long, some of them will be short. So looking at the different O&M activities, we try to group them into different groups. Some of the short ones, so inspection, for example, will not need to take a very long time. But if you need to do something like a generator replacement, you need to have a long time to do that. So what we've looked at is we've taken some existing data from the ERA5 data set, which has 1 hour readings of weather conditions. So some of the weather conditions that we are looking at here is shown here. So talking about precipitation, so that's the rain. We're also considering the wave conditions and then also the wind conditions. You need to have all these conditions right before you can actually carry out O&M activities. So we are developing this model which is combining all these. There's a lot of models which exist which maybe focus on individual environmental loads, so maybe making predictions on the wind, but this one tries to combine all those. The key thing that we want to do here is to establish what we call a go or no-go scenario. So one of the things which often happens, certainly happens in the UK and Europe, is sometimes you have an O&M team get ready and then they set sail to go and do O&M activities. But by the time they get to the wind turbine, the conditions have changed, and so they are not able to do the O&M activity. They have to come back. So that kind of scenario, we call it sail and fail. So the whole idea here is to try and prevent those sail and fail scenarios where by creating a kind of go or no-go scenario. So if it's a go, that means there's a big enough weather window for you to carry out. If it's no-go, then it shows that there's a risk that if you do set out to sail or set out to sea, you will not be able to carry out the O&M activities that you need to do. Yeah, so we have a kind of rolling window of which is moving, and basically we create like predictions in the future based on that data. So this slide basically just shows a little bit about the approach, like I mentioned. So we carry out binary classification based on go or no-go scenario, and we've got the kind of different weather windows that fall into that. So what really is happening is under the bonnet is you have all the different inputs that I talked about. So precipitation, the wave conditions, the wind conditions. And what we do is we basically create models to make those predictions, and then we set different thresholds. So for certain O&M activities, you may need like heavy lift vessels, which may need better conditions, or you may be carrying out activities where you don't need very good weather conditions. So we can set different thresholds for different conditions, and that allows us to basically identify when the conditions are right. And so we basically have, once again, the go or no go output. Okay. Yeah. So far in the project, we've used about 6 months worth of data to test this. So the data set that we have goes back decades, but just because we are at the beginning of this research, we use a small data set. Overall, in terms of the performance, we get relatively good performance of the overall output of go or no go, with about 90% accuracy. And of course, based on historical data, so we're able to check, and we hope to expand that and improve the accuracy in the next coming weeks as well. So there is a bit of work that we need to go. I'm hoping we can have further discussions around this, the approach, perhaps the reason why we went with this approach compared to some of the, let's say, conventional approach of making models specifically to predict, let's say, wind condition or like wave conditions. So we've also developed a bit of a GUI, which is kind of shown here. So basically, the GUI allows you to see a map of a wind farm, and when you click on the different wind farms, you can see the health condition shown, for example, and then you can have the go or no go decision shown for different things. So here, this is just an example. So basically, in this case, it's showing that if you want to do inspection, you can go ahead and do an inspection. If you want to do maintenance, maybe that is risky. But if you want to do like a replacement, that is not possible within the next weather window. So I think that covers it for the first work package. So I will move on to the next work package, which is looking at wake effects on offshore wind farm. And once again, because of the limited time, we aim to basically produce a proof of concept of a web-based wake prediction and power loss model. So I will move on quickly a little bit. So this is a model that or this is a tool that we've developed at the Catapult for predicting wind turbine wakes. So this is based on the PyWake algorithm or PyWake code, and it allows you to basically change the different yaw angles, different wind directions of a designed wind farm, and we're using this as part of the development of this work package. I want to show a little bit about the outputs that we are hoping to establish as part of this project. So these two graphs actually come from actual wind turbines. They are not simulations. And from looking at these graphs, you can see that on the y-axis, you've got the power ratio, which is an indication of how much power is being produced or expected to be produced, and you've got the different wind directions shown here. So wind directions, what you can see is that at certain wind directions, you get a dip in the expected power, and this is mainly caused by the wake of the wind farm near or the wake of the turbines near each other. You can see from this graph that at high wind speeds, so the different colors show the wind speeds. At high wind speeds, maybe this effect is not as pronounced compared to the low wind speeds. So our approach here is to basically develop a mechanism or for estimating how much power loss you may get from the different wind directions depending on your wind farm design. So if you've got your wind farm of a particular shape, depending on how it is or how close it is to other wind turbines, you may get severe or moderate impact from the wake from other turbines. And what we're hoping to do is to develop this model so that you are able to better apply some advanced control algorithms for wake steering, for example. So you can use wake steering techniques to adjust the yaw angle to maximize the power that you need. Yeah, so far, as I mentioned, we've got our wake model, which is able to produce the wind farm designs and able to get us to understand how the wind turbine wakes interact with each other. But when you have wind turbines close to one another, they can have a massive impact, like I mentioned. So this is a bit of an indication of how wind farms which are next to each other might interact or might influence the power generated from one another. And as part of this, this is just an initial graph. So we hope to have a more defined model, which is able to give you this particular graph for whatever wind farm condition that you have. So whether you are this particular wind farm or that particular wind farm, you'll be able to generate like a bit of a trend showing the impact of the wind direction on the power that you're generating. So that is the second work package. And the third work package is focused on port logistics. So as part of this project as well, the main work that we're trying to do is to develop proof of concept web-based GUI for offshore logistics and O&M for UK and Brazil. So far, we have been looking mainly at UK. So when we talk about port logistics, I've included some list of things that can be included in port logistics. The challenge is that we have a very small amount of time. So what we've done is we've selected some of these for the proof of concept, and the main things that we port logistics that we want to focus on is on vessel scheduling and vessel tracking. And so we've developed this tool, and this map is basically a map of an offshore wind turbine in the east of England. So this is Innerdousing, so part of Linen Innerdousing, and they have their service in port here, which is a little bit north of where they are. And what we've basically developed is this tool which allows you to do vessel tracking and optimize the path for carrying out O&M activities. So this is not ready yet, but basically the whole point of this tool is you have your wind farm with the different colors showing the conditions. So if there's a wind farm which has a fault condition or wind farm that doesn't have a fault condition, you're able to optimize how you're able to get the repair crew from your port to the wind farm, and also within the wind farm you're able to optimize the path or the path through the wind farm to make sure you limit how much time you're consuming. So there can be different things to optimize. So one of the things we may want to optimize is the time to get around. But one of the other interesting things that we also want to look at is the limiting the greenhouse gas emission, for example. So if perhaps you travel a little bit slower, if you optimize the distance between the different farms, you can reduce your greenhouse gas as well. I'll move on to the next slide, which is looking at digital twinning for offshore substation. So as part of this as well, once again, we're mainly looking at just providing proof of concept. We want to provide a bit of a proof of concept of how a visual digital twin of offshore substation would look like. So for this, I have this, which let me just quickly play. I could go a lot into detail, but I think I'm gonna just quickly. So this is a kind of digital twin platform we developed for our wind turbine, the Levermouth wind turbine. Basically allows you to show different aspects of the wind farm, so you can connect up different algorithms for monitoring different components. It can show you the maintenance records, for example, if you want. So this is where we want to get to in the end. But I just want to show you that as an option of a digital twin platform. Unfortunately, when it comes to substation, we don't actually have a substation of our own, just like we have. So at the moment, to carry out this piece of work, we have basically assumed a particular substation. Let me just skip over this. So this is the showing a bit of like the current status of the substation that we've modeled in our digital environment. So this is mainly done in Unity, the game engine, and we've connected up some. These are all fictitious AI models. This is purely because we don't have a substation, an actual substation, but this is basically showing how the system could work. In the future, we hope to establish a bit more of a complex approach like this. So this is in the same environment, but not done for a substation. This is done for robotic application. So in this case, it's still in our VDARE, but we have a robot which is basically carrying out inspection of an offshore asset. So basically, you're able to move the robot and make the recordings. There's also this page which is showing the digital twin of our lever mouth turbine. So this is the digital twin of the inside of the lever mouth turbine. And we're able to work with a company based in north of England to create this type of digital twin. Once again, because we have a physical asset. And what we did is each of these different dots on there is linked to an analytic, which is monitoring different components. Either that or it's linked to the design information, O&M information of those different digital twins. So using that, you can basically have a bit of a walkthrough. That is the goal that we want to get to. Unfortunately, because of the length of this project, we are not able to necessarily get there, but any kind of work we can work together on developing like a much more sophisticated digital twin for the offshore substation will be fantastic. The next work package is also focused on AI enhanced environmental impact assessment. So for this work package, what we're hoping to do, we only just started this work package, is rely on large language models to get a lot of data which is available already online to help us optimize the environmental impact assessment process. So the key thing here is that the environmental impact assessment process in the UK, or the consenting process in the UK, could take normally takes about 7 years to get from project conception to getting consent. It is too long a time, so we're hoping to shrink the amount of time you need for consenting by shrinking how much time you use for environmental impact assessment. So some of the key things with the environmental impact assessment is that you need to carry out some environmental measurement and then basically track that over time. But there is already some work which has been done. Usually there's work which has been done in similar areas, or be it from oil and gas or for other wind farms. So what we're hoping to do here is we're hoping to extract information which is just available from other sources, put it together and help identify where the gaps are. So if you're carrying out environmental impact assessment, you don't necessarily need to repeat some of the environmental monitoring, which has already been done by others, and hopefully that will help shrink. So this slide basically gives a little bit of like the approach that we are planning to use, and this diagram basically, yeah, shows what we're planning to construct, basically to grab a lot of information from GIS, because EIAs have to look at specific area. So we want to grab the information from that area. Luckily, in the UK, we have the Crown Estate have the Marine Data Exchange, and it's a database where the Crown Estate have collected a lot of information on environmental monitoring from different sites all across the UK, and it's all open access, so anyone can access it. So we aim to index that, create the kind of documentation, and use the LLM to generate like a report which will show you where the existing piece of work has been done and also where the gaps are, so that you're able to identify which bits of work you need to do and which bits of work has been done already. And the other work package is on concrete-based substructure. So floating wind is a growing part of offshore wind industry, and the potential for having concrete-based structure or concrete-based floating structure is very, very big. But I think one of the questions is, how are you able to manufacture these structures port side, and whether we need to build more and more and more ports. So this project or sub-project is mainly looking at, can we optimize the design of a floater, a concrete-based floater, for specific ports. So far, the key factors that we're looking at is to look at the floater design. We also want to look at some of the port requirements. So, for example, how deep the port berths are, the tugboats that can be used, things like that. And the key thing that we're hoping to do is to develop an optimizer. Partly because of the length here, we're not able to optimize across all these different, but we want to optimize mainly across some of the design parameters. So the size of the floater, and also other parameters like the draft restrictions on the port. So what this will enable you to do is to understand, if I have this kind of floater design, this is something that can be manufactured at these different ports, or if I have a different floater design, maybe it might need that you need to build a specific port. But of course, we don't want to have to build new ports to accommodate like new floater designs. So hopefully this one will help us to address some of that. So I think that pretty much covers what I really wanted to talk about. These are some of the designs of the information around the IEA 15 megawatt turbine. So that's the basis of the wind turbine that we're using for this sub-project. And I think that covers all. Probably a little bit gone over the time a little bit, but I hope you found that useful, and hopefully we can get some good engagement.
Thank you, MP, for your nice presentation. You basically cover all the possible aspects. Actually, in offshore renewables, to be able to apply the artificial intelligence, I think after this presentation we can have maybe up to 2 questions, if there's any. Feel free to ask. One question.
Good morning. My name is Enzo. I'm a public management student from here university, and I'd like to know if your work has some statement statement incentive. Here in Brazil, we have like co-op that state institution. I'd like to know if in your country, in your if your business has some like this.
So I'm not sure if I completely understand. So for ORE Catapult, we have different centers in the UK. So I talked about the National Renewable Energy Centre, which is like where we're based. But we have different centers. We are not, we are partly government funded, but we are a private organization. So we are just an RTO, but we work across very closely with government. So I mentioned things like the Crown Estate. So the Crown Estate is essentially like the owners of the seabed in the UK. They are essentially not part of the running government necessarily, but they are part of government. And we work very closely with them. So internationally as well, we don't at the moment have specific offices internationally, but we have partners all over the world, like here in Brazil with UFRJ. So we're able to have good communication or good interaction with everyone. I hope that answers your
Thank
question.
you. Yeah, but you have time during the interval to interact with.
Yeah.
Any other question? One more question? Okay. Thank you so much for your presentation.
thank you.
One question.
You could see, guys, you could see this in this activity, just 7 months. No? We are pushing more on proof of concept on that selected topics, completely different, but broad, important for offshore wind, as Brazil is an important moment, first stage, first round, soon. All these things we've thought to be applicable in Brazil. This statical fund was not for advancing UK. That is also necessary, as Ampere mentioned. But we see applicability for the developments here in Brazil. The lack of data, like we see that on ports or environmental, we could need to handle, and using study case from the data we had in ports, But is as mentioned, any other from Brazil that along the time will be, let's say, available for us can be applied. Just a detail, is UK, Brazil. But we need, of course, basically we have that data, real data. For some cases, we use that, okay? It's important to mention only.
Thank you again, Ampere. Okay. We finish the first block. We have another block, including 4 presentations. But before that, we're going to have 15 minutes of interval. We have coffee. I hope that still we have coffee and water. We tried to buy some biscuit, but all the markets are closed. I don't know what happened today. So we have something. We don't have anything to eat, but some coffee and water, okay? After 15 minutes, we're going to back to continue the second block.
I think at the time now we have to speed up some point. Ok, depois vai entrar o pessoal da próxima sessão, né? Tá. So you wanna eat something there? You wanna go out for some okay.
Nice to meet you. I have another meeting.
Professor, thank you so much for your presentation.
Falou, Milagre. Valeu. Corre lá que tá. Falou.
Okay, let's continue with the second block. We have, we expect 4 presentations. I hope that you could find something to eat outside, because you need to resist more than 1 hour and a half, let's say. And then lunch. Okay, so let's start with the second block. I would like to invite Dr. Ehsan Nikha from our group, Jero, for his presentation between 15 to 20 minutes, okay?
Okay. Good morning, everyone. I hope you find this part as interesting as previous. I'm going to talk about the AI-assisted anomaly detection for shared mooring system predictive maintenance. Okay, the main motivation behind this work is to consider that the AI can be applied in asset integrity management. As can be seen, this is the asset condition during the time usage. We have a very constant healthy state up to probable failure start and the potential failure. Up to functional failure, we cannot see anything into the real world, but from the point that failure starts to the functional failures, we have a golden time that we can perform predictive maintenance. This distance from the failure starts to the functional failure can be detected by the AI agents. As can be seen, as the time passes from the point F, P, the repair cost of the asset will be skyrocketed. So the predictive maintenance for the asset integrity management is to reduce the repair cost, and also in order to reduce the downtime considered for critical assets, such as floating wind turbines. The main objective behind this work is to shift from reactive maintenance that usually comes with the functional failure to proactive strategy by automatically identifying subtle deviation in mooring system performance before results in functional failure. As can be seen here, we have some functional failures of synthetic fiber ropes and also the stud-link anchor lines. So in order to consider that how we can build these intelligent agents that will trigger an alarm for us in order to detect anomalies before functional failure. Okay, the mooring system anomaly detection has its own methodology. As you might know, usually the real world data comes from the supervisory control and data acquisition. We call it SCADA. But in the absence of SCADA, we are going to build a fully coupled numerical model, a digital twins of that wind turbine platform, floating wind turbine platform, to generate data, and then to consider these data as an virtual SCADA to treat these for machine learning models. The first stage is to create a numerical model, 3D CAD modeling. After 3D CAD modeling, we have to gather the aerodynamic loads, the hydrostatic loads, the hydrodynamic loads, the structural dynamics. We are going to couple all of these models into the fully coupled numerical model. We are going to observe the aero-hydro servo response time series of these fully coupled model to generate the data. Then we are going to treat these data processing, the feature selection, anomaly scenario definition. Then we are going to train our artificial neural network model, which is called autoencoders in case of anomaly detection. Then we are going to train and test these models, and by performance evaluation metrics, we are going to deploy which model performs better for our machine learning model. Okay. In order to consider that the benchmark platform for considering inside the pilot scale wind farm, in this work, I had two options. The one is the Gero concept that is developed, designed, and completely detailed designed in the Gero, and also the human World-10 USS. These two platforms are considered as a semi-submersible platforms. One is for NRL, one is for Gero, with different geometrical capabilities and also different hydrodynamic performance. This is the hydrodynamic performance comparison of these two platforms. This is the Gero platform, and this is the HUMAIN, as can be seen. This is the heave response amplitude operators. This is the pitch, and this is the roll motion. As can be seen in these critical, three critical response amplitude operators, Gero performs as a reliable platform, considering the 15 megawatt IEA reference turbine. Considering the fully coupled numerical model, as I mentioned earlier, we imported the aerodynamic loads, the hydrodynamic loads, and also the structural dynamics, considering the multi-body stiffness matrix of the floating wind turbine platform, considering the blades, nacelle, the towers, and also the mooring dynamics, considering the stiffness and damping of the mooring lines. All of these models imported into the OrcaFlex, and with DLL interface, the data from the hydrodynamic, which is already calculated by the bladed imported, and the fully coupled numerical model of the floating platform can be created, as can be seen here. For the pilot scale wind farm, we are going to do the same. The 15 megawatt IEA wind turbine, considering the aerodynamic loads, rotor dynamics, tower dynamics, the hydrodynamic part for the floating body, considering the calculation of the added mass, stiffness, and damping using the Cezanne package, considering the mooring dynamics. In case we have the shared mooring system, we can have both the taut mooring lines and also the catenary profile mooring lines that can be taking advantage of both synthetic fiber ropes and also the chain. In this case, the restoring force of the mooring system can be obtained both from the geometric stiffness and also the elastic stiffness. All of these performance, all of these characteristics imported inside the OrcaFlex model. As can be seen here, this is the fully coupled pilot scale wind farm operating with the rated power. Usually, when we talking about the pilot scale wind farm, we are going to talk about the shared mooring and anchor system. This is the new approach in order to reduce the capital expenditures of the chain and the anchor, and also the operations needed to deploy these for the mooring system of the pilot scale wind farm. And also the shared mooring system will reduce dramatically the environmental footprints. For example, the subsea habitats and also the subsea nature should be preserved in case of protecting the environment. Considering the layout of the pilot scale wind farm, we respect the lateral turbine spacing and also the downstream spacing for the wake recovery. This is the pentagonal layout of this shared mooring system that 4 floating wind turbine platform harnessed with only 5 anchors. And these pilot scale wind farm taking advantage of both geometric and elastic stiffness. For interconnected turbines or interconnected lines, I use the nylon, but for the anchor lines that usually connects the connectors to the seabed, I use the chain for the catenary profile. These are the specification specification of the mooring lines and the labels I assigned in order to use them for data generation. Considering the mid-ocean condition for DLC definition, I use the Búzios field, the Brazil East Coast. I use the K-means clustering in order to filter the abandoned time series data of the wave wind. As can be seen, the 4 main clusters have been obtained out of the K-means clustering in order to be representative for the most probable mid-ocean condition of the Búzios field, considering the wind speed, the wind direction, and the wave condition. For the wave wind simulations for the DLC, I used the turbulent wind model that created in the TERP sim, the chimal wind spectrum, the 3-hour simulation of the chimal wind spectrum for the rated power. The speed has been considered as the hub of the rotor. And also for the wave, I used the Jones-Webb wave spectrum that will usually considered all C states with adjustment of the peak enhancement factor or the gamma parameter, as you might know. For the anomaly scenario definition, I defined 4 anomaly scenarios considering the losing stiffness in this line for the, as an anomaly class 1, for the anomaly class 2, anomaly class 3, and anomaly class 4, which is the complete failure of these line. Considering the dataset features as an wind farm coupled aerohydroservo response, the machine learning model can be trained to the normal operating conditions, and with defining an script and some expressions, these machine learning models can detect the normal operating condition from the anomaly detection based on the reconstruction error. I will explain in the future slides. Okay. In order to build these dataset features, I considered that 36 reference sensors can be used in order to obtain data. These are the 3-hour simulation of the surge, sway, heave, roll, pitch, yaw, the nacelle acceleration, the rotor speed in the radian per seconds, and the blade pitch angle. In the real world wind turbine operation, we might know that the platform motion can be obtained by the fused RTK GNSS board and the motion reference units. The blade pitch angle can be measured by the pitch encoder, and also the rotor speed can be measured by the shaft encoder. The nacelle acceleration also can be measured by the accelerometers. These 6 degrees of freedom motion implicitly brings information from the wave condition, and also these rotor speed and also the blade pitch angle brings implicitly information about the wind condition. The nacelle acceleration, which is the servo response, is also bring implicitly information about the coupled behavior between the aerodynamics and also the hydrodynamics. Considering that this is a normal versus abnormal condition for anomaly class 3, these are the data of a 1-hour simulation between these 2 conditions. when we have anomaly class 3. By observing and monitoring the aerohydro server response, the data of the all piloted of the all wind turbine platforms in the pilot scale wind farm, we can now start to do the data processing and performing the training of our autoencoder models for anomaly detection purpose. As can be seen, these data belongs to floating wind turbine number 1. This is the surge, sway, heave, roll, pitch here, the blade pitch angle, the rotor speed, and also the nozzle acceleration. In order to process the data, usually I use the 9 platform, which is has a very nice graphical user interface. The data will be imported by the, for example, the CSV reader. We have different kind of modules inside the 9, the data processing and data cleaning. We have the part that belongs to adjustments of hyperparameters of multi-layer perceptron autoencoders. We have modules that can be define the hyperparameters and also the structure of the long short-term memory autoencoders. We have Keras learner. The Keras is a very nice deep learning platform that is coupled with the TensorFlow. After the dividing the data into the training, validation, and testing, we can train the training data and checking with validation, and then using the testing part of the data set to test that how these models performs well considering the detection of the anomalies. Here it's some a script in order to define the variation and also define distinction between the anomaly classes. And at the end, we have some evaluation performance metrics to see how these models are performed in this scenario of anomaly detection. Considering the hyperparameters of the multi-layer perceptron and long short-term memory autoencoders, for the input layer of both models, we have 36 neurons for 36 reference sensors. That these 36 reference sensors will be observed every 60 seconds. It means that every 1 minute, each signals would be sent to these autoencoder models in order to observe and monitor the data from the pilot scale wind farm. For multi-layer perceptron, we have 108 neurons at the input layer. These are the hidden layers. This comes with the, for example, increasing, decreasing, and then increasing. And the output layer, we have another 36 reference sensors, because this is the nature of the autoencoders. Usually the autoencoders is the kind of a module inside the anomaly detection that all the sensors, all the reference sensors that has signals will be trained by the same number of input and also the output. Here I have 36 reference sensors that send signals, so I have to train all of these sensors from the input and to the output to see that how this model can train the data of each sample case considering 36 features. For the activation function of the multi-layer perceptron, I use the sigmoid, but for the long short-term memory, I use the tangent hyperbolic sigmoid, and again, the sigmoid to tangent hyperbolic. As you might know, the nature of the long short-term memory, it has a input forget and output gate, and also we have the gate for the memories. Considering the computational intensity, the multi-layer perceptron has 500 epochs, while long short-term memory is computationally intensive. It has 1500 number of epochs. And the batch size is the same between these two models. The anomaly detection strategy is based on reconstruction error. Considering that the mean square error is considered to comparing the original input value and the reconstructed or predicted value, we use this error, we plot these errors into the probability distribution. We are going to measure the mean and the standard deviation. We are defining the threshold, the base threshold and the maximum threshold. The base threshold is the mean plus standard deviation, and the maximum threshold is the mean plus 2 times the standard deviation, as can be seen here. If the condition and this reconstruction error surpass this maximum threshold, it is flagged as an anomaly. But if the reconstruction error is below this threshold, is considered as a normal operating condition. The feature scaling is very important in order to have a much better performance considering the machine learning. As you can see, this is the normal and abnormal condition for class 1. Considering that we have very undetectable deviation induced by a stiffness reduction in shared mooring lines between floating wind turbine number 1 and 2. But when we transform these data and these signals into the z-score scaling, as can be seen, it has a lot of changes that already was undetectable in these signals. So we use these signals for our machine learning purpose. This is the performance of the multi-layer perceptron autoencoder, and this is the LSTM autoencoder. This is the considering the normal operating condition, and this is considering the anomaly or anomalous condition based on the reconstruction error. This is for anomaly class number 1. As can be seen, since the long short-term memory completely separated these two reconstruction errors, so the long short-term memory can perform much better in the prediction of anomaly detection. Usually the performance evaluation matrix is based on the confusion matrix. The confusion matrix, okay, I've been going to recap it in 2 minutes. We have accuracy, we have precision, we have recalls, we have specificity, and we have F1 score of F measures that can be defined based on this confusion matrix about the prediction of the true positive, true negative, and the false negative. If we consider that this is the reconstruction of the normal condition, this is the predicted normals of the MLP autoencoders, and this is the predicted abnormal of the multi-layer perceptron autoencoder. We have the these performance for the long short-term memory as well for anomaly class 1. These are the, as I mentioned, the reconstruction error for the anomaly class 1 of the MLP autoencoder and LSTM autoencoder, and also the defined mean, base threshold, and the maximum threshold. And these are the performance metrics of the recalls, precision, specificity, F1 score, accuracy, and error. As can be seen, the long short-term memory in all of these classes of the normal and anomaly class 1, 2, 3, and 4 performs much better than multi-layer perceptron autoencoder. Thanks a lot for your attention. I hope you find this very interesting.
Thank you, Hassan, for the presentation. We're going to have the question at the end of the block. Thank you. So I'm going to invite Professor Luis Paulo for the next presentation.
pode deixar. Vamos ver se vai, tomara que rode, né? Deixa eu ver. Acho que vai rodar, vai dar certo. Como é que passa para onde? Ih, tá, foi. Passa de um lado para o outro também. Okay, I think that I still can say good morning to everybody. So my name is Luis Paulo Assad. I am professor at the Meteorology Department of the Federal University of Rio de Janeiro, and I'm also a professor at the Civil Engineering program of COP, where I'm also a researcher at the Laboratory of Computational Methods in Engineering. There is a laboratory that stays in the Technological Park of the Federal University. I think that Professor Alexander Zukov made some introduction about the lab. I will talk a little bit more about the group that I manage there, okay, the environmental modeling group. And the idea of this presentation, I think that I'm going to change a little bit. Of course, I will talk about AI models, but I will talk much more about the physical model, the physical numerical atmospheric oceanographic model that we have been using in the last 4 years to construct databases to be used in the AI models, okay? So let's go. It's here. So this is Lance, okay? As we said, Laboratory of Computational Methods Engineering. We are here inside this very disruptive building, and inside we have a lot of visualization facilities. You are all invited to be there one time. We have also a very big cluster there that now is being updated, where we used to do our simulations. And you are here just near the Guanabara Bay, okay? Just in front the tank of Labo Oceano. Okay, so we are a very multidisciplinary team. I didn't say it, but I am an oceanographer by undergraduation, but I did my doctoral thesis here at the Civil Engineering program, dealing directly with physical numerical modeling. And inside LANCE, we have, of course, oceanographers, meteorologists, geophysics, geographers, engineers, and data scientists, of course, and people that deal directly with visualization and virtual reality. And we have all of these 8 groups of research. I am the technical coordinator of the environmental modeling group, that I would say with more detail now. So, of course, we are inside the university, and so we have as the main mission to academic formation, of course, and empowering professionals in the area of environmental modeling, and idealize, execute research and development projects and innovation in the area of computational environmental modeling. I have been doing this for about almost 20 years here at the university. So these are some basic activities. All of this modeling are physical modeling, okay? But now we are just starting to do some artificial intelligence modeling also. We also have a very strong group that deals with remote sensing, satellite remote sensing data and processes. As I said, we are a multidisciplinary team, and we work in this way. We have the team from LANCE, our team, but we also have a lot of interconnection with some research and academic institutions, not only in Brazil, but outside Brazil also. And we have also some connections with some companies, small startups, medium, and very big companies, most of them with the energy sector. We have some logos of some projects that I will talk further with some of these companies. So now let's start to talk about METOcean, meteorological oceanographic information. I think that at this time now is very clear for all of the people here why it's so important to deal and to know very well the meteorological oceanographic information. If you think in the life cycle of an oil active, since the exploration to the decommissioning, it's very important to know meteorological oceanographic information, not only to do some plan, but also to the operation and maintenance of the actives. And of course, we have a lot of environmental demands and now energy transition that you need a lot to know the meteorological and oceanographic information. So, saying this, we need to know that you have some motivation, some challenges, in fact. Some of them was already told here. For example, we have a lot of global models like Area 5 that you mentioned. That is very important for us. We have the operational models that we can feed regional models, physical models, in order to have more resolution. But we have a lot of lack of spatial information, detail to use, for example, for engineering demands. And this is one thing that we try to do there in our laboratory, to do the downscaling with physical models to go near the engineering scale, okay? And we have, of course, talking about specifically South Atlantic, we have a lack of in situ oceanographic and meteorological information, especially over the sea. The meteorological information is almost nothing. We have some of this information with some operators like Petrobras, but unfortunately, they are confidential. So it's difficult for us to use, and we need this to evaluate our models. We have the limited, talking about the physics of these models, we have a limited integration of these models with local information. I will talk about a technique that we use a lot in our laboratory called data assimilation. Data assimilation basically is a technique that when you run a physical model, you can, in an interactive way, use the observation in order to bring the result of the numerical result near the observation, the real that is bring by the observation for us. I don't know if I became clear. But this is one thing that we apply a lot, but to do data assimilation, we need data. And we need also, talking about the physical, we need to integrate more the atmospherical thing with the waves and the circulation. All of the things, these processes interact over the sea surface and will also impact, for example, at the wind profile. So the ruggedness, that, because of the waves, are very important to know. The sea surface temperature also affects the stability of the atmospheric column. So it's very important to model this. This is one thing that we try to do also in our projects. And of course, the demands. Now we have some extreme events like any place around the world. Unfortunately, because of the climate change, we have a difficult to forecast extreme events. This is very important, and we need to do this in a fast way, in an operational way. And now that's why it's so important to have artificial intelligent models. We can accelerate these things. And of course, this is important because you have a direct impact on safety, cost, and operational efficiency. You need to give me some minutes because of this. So going directly to the things, of course, I'm talking about oceanography, meteorology, ocean aspects and atmospheric aspects. They are very strongly coupled, and these things must be modeled in an integrated way. Talking about the physics, talking about the scales, of course, we need to have a multi-scale physical modeling and approach in order to being near to the engineering scale to attain direct the demands, for example, of a wake effect, of a farm, a wind farm, and other things that are very important to know in a high resolution. And the other thing is that, of course, as I said, observations and physical modeling must be integrated. And only the first thing is to evaluate. How can I evaluate the physical numerical result? With the observations, of course. But I can use also in the data simulation that will give us more consistent physical numerical results of the ocean models and atmospheric models. And these most consistent model results will bring to us database, more consistent database to be used in artificial intelligent models. And of course, the last part is artificial intelligent modeling. So now I'll talk about some projects that we've been doing in the last 14 years, okay? This was a very big project called Project Azul, or Project Blue in English, that has as main goal the development of an ocean observation system for Santos Basin region. It was in fact a regional ocean digital twin system that happens in 10 years. We have all of these in situ and remote sensors giving to us data, and this data was assimilated by a set of models, circulation models, wave model, atmospheric models, and we produce at the end some dashboards to the company that was Shell. That was a paper that we published, the first paper that we published, talking about this technique that is 4D VAR, that is a data simulation technique that we use in regional ocean modeling system. There is a very popular model open code used by the oceanographic community. So, as I said, there is a concept called digital ocean twin, and we produce some dashboards for the companies, but to attend some operational demands, not renewable energy demands at this time. So this is another project, and more recently, 2020 to 2023, that we did with a very big company called Ocean Pact, and we assimilate also data from high-frequency radar antenna. This was very nice because this antenna could acquire sea surface current data in all of this area near campus basin. So it's a very powerful data to be assimilated in our model in order to have more robust data sets. Okay, so this is a very nice project, a first application here in Brazil with data assimilation using this kind of data set. This is another project that we use also data assimilation, but now at the equatorial margin of Brazil, in a project that has as main goal to attend some environmental demands there, related mainly with oil spill, potential oil spill that we have there. And so we produce a database of 1.5 years using data simulation. Now we have another project with ExxonMobil that we are producing a hindcast with 10 years for that region with high resolution. So you have multi-scale grids. The high resolution grid has for about 1 kilometer for the whole equatorial margin region. And this is what a paper that we produced. And this, by that time, this project won the ANP Prize for Technological Innovation at 2022. And now talking about AI, start to talk about AI, okay? Not too deep, more shallow, okay? But what we have been planning to do for some years ago, together with Professor Alexander Zukov, that is the AI specialist, okay, is trying to produce a huge database associated with numerical physical results of ocean current models, atmospheric models, and to use this database in different machine learning algorithms to produce not only diagnostic fields, but of course, to proceed with forecast. That's a very huge challenge. We have been learning too much. I think that we still are in the beginning of this travel, okay? But we are acquiring a lot of knowledge. This is a project that will end now in 2026 that was called the Met-Ocean Intelligence Project. Together, it was sponsored by a company called Carum Energy. And Carum has an active near the south region of Brazil. We have a lot of extreme events and the passage of cold system fronts that the wind is very strong in this area. And so they need to have, we have produced to them an operational system, forecast system for ocean circulation, atmospheric modeling, and wave modeling. But to use in our AI and to train our AI models, we produced what we call a hindcast. Hindcast is a run that we do for a period of time in the past, of course. So we produced 1 year hindcast of wave fields, circulation fields, and wave and atmospheric fields, and we feed different kinds of algorithms of machine learning, like FCNN and ConvSTM, to train them and to produce forecasts. Okay. So these are some results. I will not go deeply in this. I think that Professor Alexandre talked about some of them, but this is some, of course, some analysis, some traditional analysis that we did. What I call observation here is, in fact, is the original field of the numerical model that was evaluated by in situ measures that we have. This is important to say. So it's not only I take the model, the physical model, run the model, produce a result, and feed an artificial intelligence model. No, I evaluate evaluate the physical model results. Most of the times I use data simulation to be more consistent, to have a data more consistent, and after that I use an artificial intelligence model like GNN and FCNN model. So you can compare which model is better. But by this time, that time, we only feed, for example, to have a forecast of circulation, you only feed the AI model with circulation. But oceanographers, and not only oceanographers, know that mainly the sea surface circulation is very well affected. It's very important to understand the wind also. So we are starting now, outside this project, to train some algorithms, not only with the sea surface currents, but with the winds. And now there is another variable. And we are getting better results with our artificial model. So we are trying to bring more physics to our model. This is the things that we like to do, okay? So let's go. This is the same result, but now for the currents. And we still have only currents and not the wind. We are starting to do this now. This is another project now directly related with renewable energy demands, a project that was sponsored by Total Energy. It's ended in December of last year, and has as the main goal the development of a computational methodology to estimate the offshore wind resource in time and space based on remote sensing techniques, satellite remote sensing techniques, in situ meteorological data, atmospheric physical modeling, and artificial intelligence. So the main idea, we have in situ data, physical atmospheric modeling, and remote sensing producing the database that will be used by artificial intelligence. And of course, we have three-dimensional data sets of wind fields, so you can extrapolate with AI models also at the atmospheric column until the height of the turbines to understand the wind resource and, of course, the wind potential, energy potential. And we have, of course, a layer of uncertainty quantification because we want to develop a methodology. And what is the advantage of this kind of technology? If you have one LiDAR, for example, one sensor measuring the vertical profile, you have at that point that information. But with this methodology, we can have a volume estimation. And over the ocean is very important because it's too much expenses to have a lot of LiDARs spread over a big area to plan your future farm. Let's go. So, and what's the trouble? We have, okay, I will finish. We have a geophysical model, an algorithm that take this synthetic aperture radar images from the satellites and produce these color fields that we're seeing, the wind velocity fields over the sea surface. This is very nice because this image has sometimes an area of 100 kilometers for 100 kilometers with sometimes 50 meters of resolution. So you can have at each point or each pixel of the image, you have an information of the wind velocity and wind direction. But you have this image, you only use in this project publicly available images. So you use the image from the Sentinel sensor that is freely available for the community, but 12 days of frequency. And then you have the 3D regional atmospheric physical model evaluated by an in-situ observation that we have in an area of the coast, near of the coast of Brazil. And then you have the frequency of 1 hour. I think that in the project we start to do with 30 minutes. Each 30 minutes I have an information of the wind field. So we will use AI to fill the gaps. We're considering the remote sensing, the real observation. We fill the gaps with AI, and after that, we were able to do forecasts from next days. So this was the idea and what was developed in our project. So this is a framework. We use a WO that stays near the city of Itajaí, near the state of Santa Catarina, the southern part of Brazil. And why use this buoy? Because this buoy was the longest period of measures, continuous measures that we have freely available. So this is just constrain our project for this area, okay? After that, we run a physical numerical model to produce a hindcast, three-dimensional hindcast. These things were used at that methodology to estimate the wind fields using SAR images, satellite SAR images over the sea surface, okay? And then we use this database in artificial intelligence model to understand the different algorithms that we use, which is the better one, which is the best one. And after that, we have a layer of uncertainty quantification, as I mentioned to you. So these are some results, okay, about the tests that we proceed with the period that we have of data set that we generated. We have, of course, we evaluated, after the forecasting evaluation of different algorithms of machine learning. And this is the paper that I think that Alexandre already told about to you. We produced a multi-resolution weather data set with the physical numerical results and the remote sensing image that is available, publicly available. And now this article is submitted under review. I think that the next month we're going to be accepted. And, sorry. This is a last project that we are having now. We are ending in the April, March, that always deals with wind energy. In the northern part of the state of Rio de Janeiro, that is a kind of a hotspot that we have in wind energy here in Brazil. And in this project, we started to do that kind of coupled or connection that I mentioned to you with wave model, feeding the atmospheric model with boundary conditions, the ocean circulation model also feeding with boundary conditions the atmospheric model. And this is the idea, trying really to interconnect waves, sea surface temperature, and winds, or better saying, atmosphere, ocean circulation, and ocean waves. Okay? And why we do that? To represent in a better way the vertical profile of the winds. And we are also using remote sensing images to have an idea of that area in the northern part of Rio de Janeiro about the wind field. We acquired 2 LiDARs, and they are now operating there for about 1 year now, acquiring each, I think this 10 minutes, you have a vertical profile of wind field there. And there is a startup together with us, Tidewise, that develop an autonomous surface vehicle, a boat, and they put the LiDAR over the boat, and they're trying to certificate this kind of measures with the NFV. And that's it. My concluding remarks that I like to mention only as the last slide. Okay, I think that there are some things that are important. Our challenges that we have in the next years and the next in the future is to implement the implementation of physical metocean numerical models, doing a downscaling frameworks with high resolution along the coast of Brazil, especially implementation on development of machine learning models, enable improved predictive capability. And one thing that I think that is very important is to improve acquisition of in situ remote sensing oceanographic data is mandatory to have more development in this area. And one other thing that I think, another point that I think is very important is the introduction of atmospheric and oceanic physics in machine learning modeling. Now I'm not talking about the thing that I told you to put more variables in your framework of the artificial intelligence model, but really bring some equations that represent the circulation of current, the circulation of the winds, to constrain the model and maybe improve the capability of forecast of this model. This is one of the things that we really need to do. And that's it. Thank you.
Thank you, Professor Luis Paulo, for the presentation. We're going to leave the questions for the end of the block. Okay, we have 2 more presentations. Gabriel, I would like to invite Gabriel from NACAD. He will present. I would like to ask you to present, introduce yourself, and just a brief introduction about your lab. And while I'm trying to find.
Okay, all right. So good afternoon, everyone. My name is Gabriel Barros. I'm a postdoc researcher at the High Computing Center here at COPY. We basically work on numerical solutions of PDEs in various contexts. We've been working with epidemiological models, mostly CFD, computational fluid dynamics simulations, regarding not only the energy applications, but also environmental applications and so many more. Now, recently, we've been working with scientific machine learning, which is the use of machine learning models to deal with these numerical simulations. So I'm here representing Professor Álvaro Coutinho, who could not be here today. He is the coordinator of the AI Renewable Research Group here at COPY, and the coordinator of the Professor Alexandre Vizukov mentioned those Traverse programs we have here in COPY. Álvaro is the coordinator of the Computational Science and Engineering program as well. I'm here not representing him because I could not do that, but I'm here. That's what I could say. Yeah. So, all right. I could stall more. I mean, I have this gift of speeching, of making a very senseless speech here, and I could fill with words. I'm a chat GPT in person. Yeah, that's why I brought the computer. If we have to, we can switch the PDF. Yeah, I'll miss my animations, but, well, it happens. The animations were cool because we have a saying in our lab that when we don't have good results, we show pretty pictures. And I mean, I had a lot of pretty pictures, but it's going to be static pictures, so not movies at all. Yeah, okay, all right, yeah. And the animations, they are cool because I mean, I'm about to talk here about engineering in a more distant sense. We'll talk about PDEs and computers and numerical simulations and stuff. And so the animations, they are like, okay, this is how we know we're talking about engineering. Okay? All right. Okay, thank you, Milad. All right, I'm going to start my talk. So as I said, I'm going to talk about scientific machine learning for multiphysics fluid flows. I'm Gabriel Barros. I'm from the civil engineering program. I'm a postdoc at Alvaro's program. Let me see. I've noticed that everyone struggled with this, so it's my time now. Okay, all right. So this is our team, everyone who contributed to every paper that I'm going to show here, all the results that we have. This is Professor Alvaro Coutinho. He's my former advisor. Now he's my boss. And this is myself. And the first thing that I'm going to talk here is the basis of our lab, which is computational science and engineering. We're talking about computational mechanics. We're going to show the cycle where we have the formulation of the problem, the numerical simulations, the analysis of the results, etc. And then we're going to switch to scientific machine learning and our recent work in this direction. Okay. The first thing is that most of the things that I'm going to show here, they're not completely related to renewable energy, but it's funny that this area, we could use the same equations, we could just tweak the parameters and switch the context completely. So here, when we talk about coupled fluid flows, when we talk about renewable energy, we might have, for instance, lots of presentations here showed floating wind turbines and everything. Those are pretty much coupled fluid flows where we have to model the fluid that reaches the turbine and the structure itself. So we have a coupled fluid flow, a fluid structure interaction. We could have so many different couplings. We have structured coupling where we have the structure and the flow. We have thermal coupling in the sense where the temperature affects the nature of the flow. We have multi-phase flow where we have two or more fluid phases acting together, and reaction coupling where we could have the interaction of some chemical species that would affect the fluid flow properties. And okay, so those are lots of the things that we have been doing in our lab. Those are completely unrelated to renewable energy in a sense, but they are related to energy in a general sense. On the top left, we have a turbidity current. This is where we have sediments that affect the density of the flow and then create the motion of the flow. On the top right, we have a reservoir where we were trying to solve a problem with a two-phase flow. We have fluid structure interaction on the bottom left, and we also have two-phase flow here on the bottom right, where we try to identify the structures of a bubble. And one thing that all these simulations have in common is that they require at least a million of cells in the domain. And from a practical perspective, a million cells could be a lot or not too much, depending on the problem that we're trying to solve. But here we're talking about coupled fluid flows, which are strongly nonlinear. They are extremely expensive to solve, and those problems represent closely to real-world applications. So we need to understand what's going on, because when we're trying to solve this on a supercomputer, we might be in trouble if we don't know what we're doing. And this is pretty much what we do. The first thing that we do is that we understand a problem of interest. Could be a problem of interest for society, for any corporation or anything like that. We understand that from a physical sense. We just understand what's going on. And then we move to the mathematical perspective, where we try to model that using partial differential equations. Notice here that we have a coupled fluid flow. We're talking about the incompressible Navier-Stokes equation coupled with the transport equation. And then, I mean, this is purely math. We can't do anything with those equations, so we need to approximate them and solve them. So we use numerical methods. You could choose one, your favorite, and then as soon as you have your algorithm ready, you can just port it into your supercomputer, and then you would have the results. Oh, sorry. The results here would be a video of a turbidity current flowing in the domain, which would be very similar to the first image, but this is a never-ending cycle, because as soon as you analyze your solution, you will notice that we could improve the physics. We could add something more interesting. We could add another quantity, another granulometry for the turbidity current, for instance. We could just, this is a never-ending cycle. We just improve the physics, we improve the algorithm, we improve the HPC model, we improve the visualization, the analysis, and it goes on and on. And when we're talking about coupled fluid flow, we have the Navier-Stokes, incompressible Navier-Stokes equations, and if we want to add more physics to it, we might need to add one or more equation that would connect, would be coupled to the incompressible Navier-Stokes equation. So every time we add more physics to a problem, our system grows. And there is a huge problem with that, because algorithms that solve this approximation, they do not scale in a linear sense. So if I'm talking about 1,000,000 degrees of freedom to solve a problem, if I double it and move to 2,000,000, that does not mean that I'm going to have twice the effort. The computational cost for that is superlinear. So in the optimal sense, it's actually even worse. And that's why we have scientific machine learning now. So lots of things that were mentioned here. Professor Lispolo mentioned data assimilation. It's one of the various applications we have in this area, in this field. So we could have surrogate modeling. We could have inverse problem using a Bayesian approach. We could have physical informed neural networks, and it goes on. The thing is, the field of scientific machine learning, although it's a fancy name, it's pretty much the standard machine learning, but for these numerical simulations and the computational science and engineering cycle. Here, most of the things that we're going to show, and I'm going to be very quick because I know if you're not starving, I am, and I have 70 slides to show, so I'm going to show real quickly the results. The main key idea that I want to show here is that the things in the first half of this presentation, and most of the results are regarding surrogate modeling. All right. What is the problem that we have here? Depending on the problem that we have, we might need to optimize it, understand it, or design it. And for all of these three pillars, we have a workflow that requires us to define the physical and mathematical models, just like I showed earlier. Then we set up what are the parameters that we're going to change in the simulation. I showed one simulation. It was static, but it was one simulation of a turbidity current. We might need to tweak the parameters to mimic the real world. But we need to define this parameter space. And as soon as we define this parameter space, we can proceed to compute. And the thing is, if we're talking about optimization, if we're talking about uncertainty quantification, we need to run all of these simulations like thousands of times, millions of times. That turbidity current simulation we showed, it's a realistic simulation, but it takes around 48 hours to run on a supercomputer. If we need to perform UQ, uncertainty quantification, we might need like 1,000,000 of results. This is unfeasible. I would leave my computer running this problem, I would die, and probably my grandson would watch the results, and he would find a bug in my code. It would mean nothing. But now, when we take a look at the compute part, it becomes even more problematic, because for every time we need to run the simulations, we need to mesh the problem. This is a very expensive stage, although, I mean, lots of people talk about the nonlinear solvers, but depending on the problem that you're trying to solve, meshing can be a struggle. And then you have to solve for all the time of your simulation, a lot of nonlinear equations which do not scale linearly. Notice that the problem scales in a superlinear fashion, and this is optimal. And when I mean optimal, it's idealistic. We cannot reach this level. We cannot reach this number. It's always quadratic, and we could have something superlinear with the proper algorithms for specific problems. And that's where we have scientific machine learning to help us. And the thing is, as soon as we introduce a surrogate model in the sense, the idea is, instead of solving this problem for millions of times, we could select a number of train where we would have some samples. We could run some simulations, not a lot, but some. And with this small number of simulations, relatively small number of simulations, we would collect this data, we would choose the appropriate metrics, we would perform a generalization study, and maybe add physics to the model, and then in the end, we would have a scientific machine learning model. And this would probably help us because for all the remaining simulations that we would have in the parameter space that we queried, instead of running the numerical simulations, we would perform the inference on a scientific machine learning model. The inference wall time for this model is way, way lesser than the numerical simulation. We would need 48 hours to run the numerical simulation earlier. Now we need probably like a week to train this model, and then it would generate us the output in 5 minutes. So we have a lot of effort to train these models. They are usually represent a number of simulations, but then once it's trained, we can just perform the inference. All right, here we have the application. So pretty much that's the part of the presentation where the key that I wanted to show what we're doing is what the previous slides. Now what we have been working, we have turbidity currents, thermal flows, and multi-phase porous media flows. And I'm going to go very quickly here in our contributions. The first thing is on turbidity currents. We used, this is a very cool picture. It's from a paper from Nature where they cited us. On the left is photography showing the turbidity currents. On the right is our numerical simulations with the appropriate color map. So it means that we are solving the equations, and we are pretty much mimicking the nature. And the regions where we have the positions of these turbidites, they're usually regions of interest. So that's why it's important to know how the sediments deposit, because it's usually interesting there. We have aquifers, we could have pretty much of interesting things in the subsurface. And what have we done here? We have a linear and a nonlinear model. We have tried a lot of things. The first thing is using a model called dynamic mode decomposition. This is cool because for any kind of data that you have in space and time, you could set it in a way that you could extract some modes that dictates the dynamics. With that, you can analyze what's going on with your data. Not only that, is that once you extract those modes, you can infer things. You can predict in time. You can perform diagnostics. You can perform a lot of things. This is a very interesting model, which is very fast. It's a linear model. It has a lot of limitations, but it's pretty much used in a spatial-temporal time series. And the thing is, we need to compute the pseudo-inverse of all our data, and our data is very large, as I mentioned. So one thing that we use is the singular value decomposition for that, and the DMD relies on throwing away part of the information. We thought, okay, we usually perform SVD, we truncate and throw away a lot of the data and reconstruct the data, throwing away part of the variance. What would happen if we use data compression here? So we're already throwing away a lot of information. Let's throw more, but we want to optimize. We want to make things faster and to save space in the disk. And that's what we did. We used compression on DMD, and what we noticed was that, okay, this is pretty much what data compression is. You have any kind of information, you apply compression, and then it's like a WinZip, WinRAR, everyone done something like that. We use that on scientific data to throw away. We don't need to store all of the numbers on all the floating point numbers on data. We could just throw away some of it, and then we can take advantage of all of the benefits that we could have in our computers with that. Simulations, computations go faster. We require a lot less space and disk. So I'm skipping all of this pretty much details. But what we have done was applying dynamic mode decomposition with different data sets that had data compression. And we noticed that we could save up to 100 times the space and disk in terms of storage with pretty much no cost regarding the singular values. Once we reconstructed the solution, we noticed that the quantities of interest pretty much were the same. So most of the things that I'm going to show here are related to high-performance computing and numerical simulations and stuff. So this is what we have done for the same thing, but for a bubble rising. And notice that we're also using here in situ visualization for the data. So we have numerical data from numerical simulations and visualization data as well. And we pretty much published our results here in this paper for engineering with computers. We also studied the use of adaptive mesh refinement. This was a video where we would have some bubbles showing up and the mesh would coarsen in this direction. We noticed that we could take advantage from using adaptive mesh refinement in regions of interest. We reduced that number n. That is our problem that we want to solve in any case. We use data projection, and again, we noticed that DMD could be used. I mentioned earlier that some of the equations that we use for some problems could be easily ported for other problems. I mentioned turbidity currents, bubble rising. Here we have an epidemiological model. Here we measured how COVID acted on the Lombardy region in Italy. So it was one of the most affected regions in Italy, in the whole world actually. So we had a good, reliable data to work on, and we built a model on that. And we use scientific machine learning to predict for the next 14 days. On the pandemics, it was a good strategy to have quick computations to predict in the future on a time horizon of 14 days. So again, the bottom line here is that dynamic mode decomposition is a quick linear model that we could have on some spatial temporal data that could predict, depending on the physics, with some certain accuracy. And again, we published that, our results in engineering with computers again. And also, one thing that we thought is that we need to perform some parametric exploration on turbidity currents. Instead of using linear models, we used nonlinear models as well. Here, we changed the slope of the turbidity current. So if we had an animation here, we would see that they behave completely different depending on the slope. And we fed that to a neural network so that we could predict for a given slope and for a given time instant what the solution would be. We had to add two dimensionality reduction techniques to come back from the physical space into a latent space, and then we would predict the latent space. So we need to, I mean, those solutions will have that number n that I mentioned. They would have like millions of degrees of freedom. We would reduce that to, depending if we use two-stage dimensionality reduction, it would go down to like 16. And then we would fit our neural network to these 16 latent coordinates. And we noticed that, results were good. They were slightly delayed in terms of the dynamics. And we fixed that using DTW, which is a metric, specific metric for time series, where we measure how the signal is close to each other if they are somehow delayed. They could be translated or they could be shifted in this direction. And we noticed that the evolution of the current was pretty much going well in this prediction. Again, we published this last year in Finite Elements in Analysis and Design. Now, no more turbidity currents. We have the Rayleigh-Benard instability. Again, this is a coupling that concerns temperature. So we have temperature and fluid motion. Basically, we have a plate which is hot at the bottom and cold at the top. So we have those billows that appear here on the visualization. And again, we use the results on the neural network. The results are pretty much the same. Oops, sorry. Pretty much the same for the other case. And then one thing that this is interesting, although with no animation, it's pretty much the same figure. But depending on the scale of the problem, we might have some issues. Here we have two thermal flows with different Rayleigh numbers, and they would behave completely different. I think I would have some images. Okay, here is 10 to the 6. So we have these billows in a larger scale, and this is 10 to the 10. So it's very small. So we were working with beta variation autoencoders to capture all of these modes so that we could generate more data in the sense. Beta variation autoencoder is a Gen AI technology that we were using to generate data so that it could work in a synthetic way to provide data for another scientific machine learning model. Finally, I'm going to skip this. This is a paper that we're working. Our reservoir simulation, we are working on the SP10 benchmark, but our goal is to go to the SP11 benchmark, which talks about carbon capture and storage. So here we're talking about two-phase flow. It's actually oil and gas, but our goal is to shift this to carbon capture and storage. And the thing is, we have this reservoir where we inject gas, and we have oil producers in the corners of this domain. And one thing is that we're using a technology called neuroperators. And neuroperators are very good in generalizing PDEs, so in numerical simulations in a general sense. And we were struggling here because we actually had to solve this problem for a 2D problem. It worked well. We spent a lot of GPU memory. We have a NVIDIA H100 in our lab, in our cluster, where we used to feed. It's pretty much a state-of-the-art GPU. And we noticed that it worked for a small case, but we want to solve real-world problems. And wait, OK. So we need to deal with these large tensors. So every time we increase one of those dimensions is a nightmare. And when we try to solve that for a large reservoir, one thing that we noticed is that we had a huge problem. We could not fit that in the GPU memory. So, I mean, we have a state-of-the-art GPU. We have to solve a problem that is medium. We're talking about 1 million degrees of freedom. It's not super large. And it could not fit on pretty much the best GPU that we have in the market. So we could not fit one sample. This is a huge problem because people are selling neural operators in the literature like they work perfect, and they do not scale. And we want to scale. We want to solve real-world problems. So one thing that we have done is to decouple the problem. Instead of solving a Fourier neural operator, which is a large, expensive model, we split that into two subnetworks. One deals with the time, the other one deals with space, and then we coupled back them at the end so that we can generate the predictions. And now it fits on our GPU. We can use 2 as the batch size. We could not fit even 1 sample earlier. Now we can fit 2. And we use pretty much 20 gigabytes of our H100, which has 94. So we could even have more in the batch size. And in the end, we could predict the evolution of the multi-phase flow and etc. This is under review. And that's pretty much it. I was really, I went faster than I should on the numerical applications. But if you have any questions, if you are interested in neural operators or scientific machine learning applied to numerical simulations, you have my email here. You can reach me anytime. I'll be glad to take answers. So that's pretty much it. This is the acknowledgements for everyone who was involved or financed, or pretty much everyone who was working with us. And that's it. Thank you very much.
Thank you, Gabriel. You really covered a really interesting research line led by Professor Alvar here at COPY. Thank you so much. And The next presentation, to close the second block, I would like to invite Guido from Matsis. Matsis is a startup from our former students, and now we are initiating a collaboration with them, especially in AI and digital twin and offshore wind. So I think it's here. Okay.
Well, good afternoon, everyone. My name is Guido. I would like to thank Professor Milad for the invitation, for the little briefing about us. So I'm from Matsis, and here it is. I'm from Matsis. We are a startup here in Rio de Janeiro. We are here incubated in the National Institute of Technology in the center of the city. And we provide technical and scientific solutions for development of new products. And we have three main areas. We develop products in additive manufacturing, advanced materials, and digital twins. And these solutions that to develop, they meet the global innovation demands within the concept of open innovation. So this is the team. There's me, there's Cristiane and Lucas over there. I'm responsible for the mechanical engineering area, Cristiane for the materials, and Lucas is our data science. He's the expert for the AI area of the company. But not only the three of us, we also have more people on our team. We have Pedro, who is our developer, Luciano, who helps us with the numerical simulations, especially mechanical ones. We have Raquel, who is our project manager. We have Anna, who is our help us to develop our legal structuring with all the innovations that we have. And we have Josiah, who help us in the business intelligence. So basically, we as a company, we connect to the market in three different ways. The first of all is we provide specialized technical service in different areas, as CAD modeling, numerical simulation, 3D printing. We also have another way of connecting to the markets as partnership in research and development projects, helping to bring the knowledge from the universities and research institutes into the markets. And we have our third, and for today more important one, which is our solution digital twins. Our proposed solution is hybrid based, which means we have both data and physics coupled. But we're going to talk a little bit more in a minute. So once we thought about making digital twins, we decided to start doing by wind turbines. Why? Because wind turbines, they are complex and dynamic systems, and they have many issues with matters of maintenance. We saw that predictive diagnostics is a really relevant topic, wind turbines. We saw in the market some other options available in the market, but we saw that they are still limited to alarms and basic statistics. And we saw some data of the market. We also saw that in the markets in the wind turbine onshore is around 80.5 billion globally. So we thought you can maybe put our solution inside of these markets. So our solution that we propose is a hybrid one, so we combine both physical and both data. So how does it work? We use some numerical simulations to generate some data, and use also this data alongside with some telemetry data and some environment data into the model, so we can make predictions on how the asset's going to be in the future. And based on this prediction, we can make a diagnostic. We can calculate some health index of the assets and decide either it requires or not some attention. And in the future, we want to have a third model, which is the control, that based on the diagnostic, which kind of action we should take into the assets. So basically, our solution comes through this flow. First of all, define the assets, which is the turbine we're going to use. Our focus nowadays is mostly on the onshore turbines, but we want after to expand to the offshore turbines. So first we define the geometry, the model. We have the geometry of the components. The second one is the acquisition of data. So, as I said before, we need some data from telemetry of the working of the component. You also have some environment data from where the asset is, and also data from this numerical simulation. And then you combine all of these into our artificial intelligence, where we can run our diagnostic and predictions. And afterwards, we can also use this AI to simulate some what-if scenarios. We can gather more data if we simulate some conditions that are not typically operation. Because either our data in our assets, it's very biased. They're like, it's more frequent that the turbine works than it doesn't work. So the simulation and the AI could help us to generate those data in some not normal operation. All of this data we're going to have in our back end in our database. And we're also developing a front end for the user. Nowadays it's a dashboard, but we're planning to expand it to make it more interesting for the user. In our dashboard, you can see all the farms that we have access. Inside of the wind farms, you can select which wind turbine we want, and inside of each turbine, each components, and see how the telemetry data, how the data we have is at the moment. So we want to make it, to increase its TRL is to make it better for the markets, but for that we're still looking for a functional prototype so we can validate our data, so we can make technical validation and also making a relevant operating environment. Also we can work on the real-time data pipeline, so we can have data in real time coming in and out of our solution. And also we need to improve our front end to improve some usability, clarity, and overall user experience. We believe that the solution has some good values for the market. We believe that, as I said before, the solution C nowadays doesn't have the physical modeling coupled. We do believe that once you couple the physical model inside of the solution, it's going to be better to predict failures, so we can optimize operating parameters and increase some energy efficiency. And the solution is also aligned with the NIP, Nova Indústria Brasil, the National Energy Plan, and with some sustainable development goals. Wait, sorry, what happened here? Okay, so as I said, the solution we believe is going to be able to reduce maintenance costs, to reduce the unplanned downtime, to increase efficiency, to prevent some failures, and save some costs on failures. We also, from the market, this is the data from digital twin as a whole, thinking about digital twin not only in wind turbine, but also in other kinds of markets. We see that the market, the global one, the TAM over there is $120 billion in digital twins worldwide. We do see that inside Brazil, the area of the digital twins could reach about $10 billion, and we believe we can reach a share of this market of about 150 millions. So as I said, nowadays we're thinking about the wind turbine, but we also think about expansion for other complex accesses. But as I said before, we're thinking about onshore wind turbine, but once we think about offshore, there are many more challenges with the offshore. The first one, obviously, is the winds is much stronger. So we require larger structurals because we want larger turbines to get more power from the wind. So we have also higher loads, higher structures. Also, the environment is much harsher because we have currents, we have waves. Also have problems with corrosion with the assets. The system of the offshore wind is also much more complex because of the foundation. The onshore has a fixed foundation, while the floating one has a more dynamic because it's floating. And also the installation and maintenance is much more complex, much easier to reach and install a wind turbine onshore than one offshore. When you think only about the digital twins challenges itself, when we migrate to offshore, we see that nowadays there's still not that much real data available when compared to onshore because it's much newer. So when you think about data science, AI, this can be a limiting. Also, as I said before, the physics are much more coupled because not only we have the wind and the structural, we also have our hydrodynamics and also the mooring systems. And also, this might be a problem because the wind turbines are offshore, so the real-time data is a little bit more expensive to install. And I brought here a little bit graphic of how offshore turbines possibilities in Brazil. Brazil has a very extensive coastline, about 7,000 kilometers. And we see the wind is most strongly on the northeast, on the southeast, on the south of Brazil. So these are 3 good regions for installing offshore wind turbines. And we see that the potential to be installed is around 1.3 gigawatts. So it's very interesting for us. So basically, just to finish here the talk, to be brief, because I feel like everyone's starving for lunch, I'll be real brief about our history. We started here as a startup. We've been talking about since 2020, but we've started officially in 2023, the CNPJ. But we've got some founders from the FAPERJ, from our founding association here in Janeiro. We've been through some accelerating with Energias, with go-to-markets. We got a reward from Unicamp, from inventors. And nowadays we are coupled with IUP, which is a hub for startups from the IBP, which is the company from petrol here in Brazil. So thank you very much for your time, and thank you.
Thank you, Guido, for the presentation. I hope that we can establish a good collaboration between our team and Matsis. Okay, we came to the end of the second block. We thank you for those who are stay with us by the end of the workshop, and those who are watching us by the YouTube channel of the copy. Eduardo, I would like to know about your final comments and some conclusions. I think that what we showed here was the objective was to show the competencies and of the copy in AI. As you saw the presentations, there are different initiatives, projects, basically applied on oil and gas. And of course, we showed some other projects applying in renewables. So we have this theoretical basis and the actually competency to take advantage of what we have in terms of AI, the human resource, to be able to apply it on renewables and specifically offshore renewables. I think that this collaboration with Catapult could help us to have a deeper look at this kind of application. Yeah.
Thanks, Milan. I think we mentioned that after the 4 presentations should be some questions, no? Perhaps, or not basically a question, no? From my side. Was as we like Ampere could explain about the activities in collaboration with FRJ, no? How you in your research activities could see that should be next, no? Or more collaboration synergies. So this is also important. Of course, Ampere and the teams, no? We advance in some strategy like a proof of concept that you could follow, no? Maybe of the constraining time, no? But one idea of the statical fund also looking ahead. So what we can do next? Identify that. Of course, we have like myself, like I'm at Catapult. I'm let's say country lead for Brazil, no? There are other colleagues, country leads of other countries, no? Like Vietnam, we have guys in Chile, in Poland, Australia, in many countries, no? And also we have Milad, no? Milad can be our bridge of connection for opportunities. This is something really important. We have a MOU signed, no? Means that there are lots of opportunities we can identify, discuss, because next fiscal year, no? Because in UK, the fiscal year starts in April, no? So it's also time to think about what should be next. It's really important. And the examples that in your research and your groups grant and in future activities, it would be great just to think about for discussions of potential opportunities. That's a long way. We are thinking long-term things, And being here, myself and Ampere, would really great to see and appreciate your research. We see many, including also your startup company, so it's really interesting. We have similar examples in UK, and also in UK, I think Ampere can say more. We incentivize that. One of the missions of Catapult also is at several levels of mid or SMEs, companies, startups, incentivize. We have some fundings, we have some things that's promoting that in the strategic areas. So this is also important, knowing about your initiatives locally, and thanks for sharing yours, and all other departments and our researchers advancing more and more. That's I just want to thank for that opportunity to be here, from my side. I appreciate it, and be say available anytime. So we have strong connection, myself, Edivaldo, and also Milad. Anytime if you need something more about us, and also welcome to visit us. If you have a chance to go to the UK, please do not hesitate to contact us. We can visit our labs, their center of robotics and digitalization teams, Levermouth turbine. Also, we can have a chance also to see a real turbine. So that's Catapult is open for that. We received several missions from Brazil or from other countries. Important for you to know that. And it's just the beginning. We are early stage, but it's promising. Yeah, we think that we have a really strong and continuous collaboration with you. Okay. And now I think Ampere want to say something about this thing. Thanks for it. Thank you very much.
Yeah. Thank you very much. Yeah. So fantastic presentations showing some of the capabilities of copy and some of the follow-ons from research here. So I think it's been great. And Valdo mentioned the fact that at Catapult we play different roles. So obviously supporting bringing technologies from low TRL to high TRL is one of the key roles. We do that working with academic partners and SMEs as well. So the whole aim is we want to improve and develop offshore renewable energy. So a lot of the work that we've seen here today goes to help us do exactly that. So we are more than happy and more than open to help and collaborate. We've got different platforms, as we've described today, to help. So be it with our academic links, or be it with our test facilities, or the Levermouth turbine, which has like operational data which can be shared. We are able to kind of work across industry, different scales, and we are open to collaborate. So far, we've been doing great work in terms of our collaboration, setting out the beginning, the early steps, but hope to collaborate even further in the future. So, well, thank you very much for listening, and thank you very much once again, Professor Milad, for hosting us.
Thank you for coming, and let's continue working on our collaboration. Thank you. Obrigado.